Good morning, good evening, everybody, for wherever you are, and welcome back to the second day of Beyond the Basics, the Potential Role of Advanced Nuclear in Alaska virtual workshop, sponsored by the University of Alaska Fairbanks, Alaska Center for Energy and Power. I'm Gwen Holdman. I am the Chief Scientist at the Alaska Center for Energy and Power, and I'm your MC for this workshop. I want to start out by yesterday we had a little bit of a poll question about where people are participating from. So I thought it would be nice to kind of share that here. This doesn't include multiple. This is just pins for the locations of some of the folks. So you can see we actually had quite a few from California, from across the lower 48, and then lots of different locations in Alaska. I'm actually calling in. Yesterday I was in Helsinki. Today I'm in Tromsø. So I'm actually joining you guys from an evening time zone today. Anyhow, thanks to all of you for making the time to join us. And I just want to acknowledge for this workshop, and I mentioned this yesterday, but for those of you that didn't join us yesterday, that nuclear is a really broad topic. It's pretty complicated. And we're keeping this workshop pretty focused on current advances and activities, especially those that pertain directly to Alaska. So we acknowledge just right up front that there's a lot of important topics like nuclear waste disposal, nuclear fission. These are just a couple of topics that came up yesterday. The history of nuclear use in Alaska, nuclear mining, uranium mining. Those are things that we are not touching on, even though that they're important topics here. So as part of our goal of trying to educate the Alaska public and create opportunities for dialogue, we are planning to relaunch the Alaska Nuclear Energy Working Group, which is something that was active for a couple of years, but we haven't held any meetings for a while. And so I'm really hoping that some of you may join us for that. The first meeting is going to be on February 24th, and we're actually going to be focused on nuclear waste management broadly, and then also highlight Finland's Onkalo long-term repository for nuclear waste, which is the first geologic storage site anywhere for that long-term storage of high-level radioactive waste. So you can sign up by scanning the QR code that actually takes you to a survey for the working group. So it asks you some questions in terms of the types of speakers and topics that you are interested in for that. If you fill out that survey, we will sign you up to receive additional information for the working group. Okay. So this again, and I don't want to spend too much time with the preamble, but this is part of this broader workshop series, Continuing Conversations. It's a virtual workshop series, and we're taking these deeper dives into these important topics that are leading up ultimately to the Alaska Sustainable Energy Conference. This is the third one. We've had two leading up to that. All of the materials for those first couple are available online, as well as workshops that we've had in the past. There's been a lot of different topics. And so that might be something that you might be interested in going back and revisiting. All of the materials from this workshop should be available within 30 days, hopefully a little bit less than that, of the end of the workshop here. And then our fourth and final one is going to take place on April 1st and 2nd. And so these all, again, lead up to that Alaska Sustainable Energy Workshop that's going to be held in person at the Dena'ina Civic and Conference Center in Anchorage, May 19th through the 21st. So for our day 2 agenda, we are going to start off with Adrienne Collins giving us an update on what's happening at the National Reactor Innovation Center, NRIC, at Idaho National Lab. That's going to be followed by hearing from Oklo about their progress and current milestones for the Eielson microreactor project, and Brian Gitt will join us for that. Afterwards, we're going to transition after a break to discussing some of the economics of advanced reactor technologies. We've got 2 speakers for that session. They're both from Idaho National Lab. Hayden Bryan will start us off with an analysis of the Idaho National Lab completed for the Railbelt grid, and that's going to be followed by Botros Hanna, who's going to be discussing a microgrid or a microreactor costing tool that he developed. So that'll be at 10:30. And then after that, we'll wrap up with a slide that includes several Alaskans, as well as a collaborator from Canada, from Saskatchewan, who actually has some familiarity with uranium mining in that province as well. But we're going to be talking a little bit about what would it take, just kind of do a little bit of a synthesis of what we've heard during this workshop and discuss sort of what next steps could look like. And I just want to remind everybody that a detailed agenda and a complete speaker list with all the bios are available in your attendee packet. I'm not going to be reading all of the bios verbatim through the course of this. Okay, so if you didn't have a chance yesterday, go ahead and share your name and the organization, or even if you did, go ahead and do it again with your that you're with, so people can kind of get a sense for who all is here and what you're interested in learning. And so we're going to do Q&A immediately after the speakers. And so what would be great is if you guys can just drop your questions into the chat. Just make that available to everyone, and then I can go ahead and pick up those questions and sort of curate them for our speakers. If you have any issues during the event, you can chat the event support, which is kind of like a drop-down tab there, directly, and ask them for help if you need that. Again, the recordings are going to be available at the Alaska Sustainable Energy Conference website. And we're also going to make, I think, most of the PowerPoint decks available as well, unless there's any speakers that have a concern about that. But so far, I don't believe that any of them have. So with that being said, I would like to go ahead and start our first, with our first speaker today, Adrian Collins. He is the Deputy Director of the National Reactor Innovation Center at Idaho National Lab. He's been with the lab for 37 years. I actually went ahead and did the math there. So that's back to 1989. I was kind of curious, Adrian, whether you were there when EPRB2 was active and things like that. So anyway, that's a long time at the lab. But right now, I am very eager to hear some of the updates on what's happening at NRIC. So, and I'm sure you'll give us a little bit of an update on exactly what NRIC is doing. So, thanks, Adrian. I'm going to turn it over to you. We've got about 30 minutes for your presentation or so, and then we can jump into Q&A after that. Welcome.
Thank you, Gwen. Thank you, and thanks for that introduction. Yeah, I have been here for 37. I think this is going to be my 38th year. Just pretty much grew up here, and actually started in 1987 here at the site. But then I had a couple years break of service there. So your calculations was correct. But anyway, it's been an exciting career. Yeah, as Gwen said right off, I'm with Idaho National Laboratory, and I'm the Deputy Director of the National Reactor Innovation Center. And we'll talk a little bit about what that means and what we're doing. Our remit is really to partner with industry and deploy advanced nuclear at the speed of a startup. So we're making every effort that we can to move fast, because industry in general is moving fast right now. And again, we'll talk about some of the things that we're doing to try to keep up. So National Reactor Innovation Center, as NRIC, as it gets referred to, really launched in fiscal year 2020. It was part of the Nuclear Energy Innovations and Capability Act, which was 2017. Took about a year or so to get that signed. And first funding, when it rolled around, was the end of calendar year 2019 or the start of year fiscal 2020. So that's how long we've been in existence, and kind of where our roots go back to. We're part of the Department of Energy's Office of NE5, which I believe is Advanced Reactors. And our goal, all things done, is to partner with industry, right? And bring the laboratory assets to those partners in ways that we can enable their progress. And typically that's through either the laboratory expertise. Those are individuals, might be nuclear safety, for example, is a great example. It's an area we can help a lot with. and then bring infrastructure also to those partners. And that means a range of different things. We're actually building out facilities that I'll talk about a little bit, where industry partners can bring their reactor tests in and operate them. We are building glove boxes for more experimental R&D type activities. We're helping just on the engineering side. We're number of entities are coming in and actually building here on the Idaho National Laboratory, and through NRIC, we're part of that. So it's really leveraging what the government and the National Laboratory has to help move these reactor developers forward. Two areas that we kind of focus on, very broad areas. One is the advanced reactor testing. And so that's the test beds that we're going to talk about that we're kind of building out. It's siting of advanced reactors that I mentioned here on the laboratory, but not necessarily in one of our facilities. It's development of experimental facilities, glove boxes, little hot cells, that type of thing. And then we even have a virtual test bed, kind of a modeling and simulation area. All of these things were developed right out of the gate. One of the first things we did in NRIC was do a gap assessment, where we engaged with industry to the extent we could and tried to understand what they saw as the gaps going forward. So this is back in 2020 timeframe. And then from that, we kind of put our portfolio together of what we needed to go after to address those gaps and help them move forward. The other thing that we do is kind of addressing, we call it costs and markets, right? So how can we help bring the costs of construction down, the costs in general to development within these industry partners through applications like digital engineering, perhaps. And then other markets that are out there that we're engaged in, maritime is a great example of those. So those are kind of broad pictures of the things that we go after. So again, kind of reactor testing and addressing costs and markets. So in that theme, the number one highest priority activity that we have in NRIC today is the build out of what we call the NRIC Dome test bed. Dome stands for Demonstration of Microreactor Experiments, and it just happens to be it's the old Experimental Breeder Reactor 2 dome itself. For those that are aware of EBR2, I mean EBR2 operated from the late 60s to mid 90s, about 94. So it had about 30 years there, give or take, on how long it operated, and then it was kind of put on a standby and later D&D'd. And the dome facility itself was actually slated to come down at one point, but Idaho National Lab worked with the Department of Energy, and we ended up kind of preserving the dome, maybe as a historical monument. At that time, we didn't necessarily see NRIC and these advanced developers coming, but that's where we ended up, and it's really just been fantastic now to be able to kind of refurbish that dome, reestablish it as a test bed, and it doesn't run its own reactor inside of it anymore, but it'll hopefully be running a number of these micro reactors as we go forward. This rendering here is a rendering, but we're starting to look very close to that. The construction was slated to be finished. We started November of 24, I believe that's real close. We were going to finish about January, February of 27, and we, based on, again, the desires and needs of the reactor developers, we've moved up that entire construction schedule. And we did that early summer of last year, 25. And right now we're on schedule to complete the construction and the dome build out by the end of March of 2026. So we're just a couple of months away, right? So we advanced about 2 months just in construction. been very aggressive, a lot of effort put into that, but again, our remit really is to work fast, like the developers are working fast, and this is just one of the things that needed to happen. So we're on schedule to do that. Dome again. If I can just take a second, I mean, it looks big. It's about just under 80 feet. Yeah, we say 78-foot diameter across the floor space here. So think about many of these reactors that might coming in, something resembling the size of a cargo container or Sealand container, right? I mean, you take up the floor space pretty quickly. But next picture just shows some of the demo, I mean, just of interest, right? This is, when we kind of started construction, 2025, start to build out. This is a picture right here of the inside of the dome. We've had to cut right through the shell of the dome, right, to put a number of penetrations from services to utilities to support systems for the microreactors when they come in. So, and things like that, I mean, have been challenging in itself. You think about maybe remodeling an older home, right, and all the unknowns that you come into when you start to tear things apart and redo things, right? So we didn't start with fresh greenfield site or anything. We started with this, and we worked through those challenges. Just things of interest, maybe like this picture right here shows a penetration, and you can see up in the top right here, this is the actual dome hatch, we call it, but it's a big entry door where the micros will come in and out. You can see the curvature that's on that, right? So easy to engineer that. What wasn't so easy is that's a more perfect kind of curve than what's on the dome itself, right? So the fit up had to be challenged. So things like that have just been challenging, but we worked through them. We're on schedule. Things are looking just fantastic. Again, it says right here now scheduled March 31st of 2026. So we're just months away. But when we think about the dome and testing in there, I mean, it's not just, hey, here's a facility, bring your reactor in and you can operate it and then go away, right? I mean, it's more, we call it kind of an ecosystem, because there's really a much as a front end and a back end of that, and it's very extensive, right? So we look at TRISO fuel manufacturing. I mean, that's what's coming into the dome. The fuel can get shipped in. We've set up storage here on the INL, not right next to the dome, but on another facility in close proximity, where fuel can come in. It can be stored prior to actually getting loaded in the reactor. Now, some developers may have that exact pathway. Others may have a different pathway. So we're trying to anticipate and work with what we know to make sure that those pathways exist so they can be successful. So, for example, Radiant, that's the one that's actually scheduled to start coming into the dome. And we'll talk a little bit more about it here starting in April of this year. So they'll come into the dome. They're going to operate notionally somewhere about a year of a schedule there from start to finish. We're providing shielding. So this is modular shielding that can be set up kind of around a reactor test in there, depending on the requirements. Some developers will need that, some will not, but we'll have shielding that can go around their experiment. When after they've run their experiment, there's a cool down period, right? Probably several months. And then we'll remove the reactor test itself out of the dome. And we've got kind of we're calling it a cool down pad, but it's a place where these reactors will go. They'll set on the pad just adjacent, not too far away from the dome anyway, and then take a period of probably several years, right, where they kind of cool down and can actually go through a defuel process. And so we're working another facility here on the laboratory on the INL. We'll actually defuel those reactors. The used fuel can be put in. This is very old picture of these are essentially silos in the ground, and a number of different fuel and scrap is stored in them now. But the reactor developer fuel will also get stored in those. And then, of course, the final things, parts of the reactor will probably go to disposal. So that entire ecosystem has to be put in place and is being put in place as we speak to support these tests. I mentioned Radiant was scheduled to come into the dome. So we actually went through a scheduling process last summer where we solicited from all the developers that wanted to come into the dome what their kind of an application to come in, and we went through those and laid out a schedule of how the dome will be utilized. Radiant, in this case, in their Kaleidos demonstration unit, is the first one that's scheduled to come in. Kind of some key dates around that: the NSDA, PDSA, DSA. These are nuke safety documents that they're in the process of completing. But their KDU is scheduled right now to arrive middle of April. Fuel it by the end of May, and do a criticality on that by June 18th. Again, that coincides with many of us think about the July 4th criticality dates that the president put in place. So that's kind of the overall schedule. And again, just kind of a rendering, but the rendering's probably not too far off of what things will look like when they start arriving. Another one of our test beds is what we call the Laboratory for Operations and Testing in the U.S., or LOTUS. This is actually kind of in a transition, so I hesitate to talk too deeply on where this is going, but I think it's of interest too, and so we'll hit on it. And that is the LOTUS facility is essentially reestablishing capabilities within what was the old zero power physics reactor. It's in the same fence kind of site area as the dome. It goes back to Argonne National Laboratory days that used to operate the zero power physics reactor, and that's been shut down since the 90s as well. So we're going in and kind of reestablishing that as now another place that reactor developers can come into. So this is a rendering, again, pretty good one. It's very close. The LOTUS, though, is a line item construction project from Congress. And we actually went out on a construction bid for that. So we moved through the critical decision process of DOE Order 413.3B, and the plan was to award a construction contract last November of 2025 with about a 2-year construction period to build this out. When we got the construction bids, and along with some other things, I mean, the cost increased from what was originally envisioned for this. And we're currently right now working with the Department of Energy to look at an alternative to, rather than reestablish this in the LOTUS, the old Zipper facility, establish LOTUS as a new facility, which we believe we can do significantly less expensive than trying to put it into Zipper. So we're right in the middle of that. I don't really have anything to share on that other than just maybe a heads up that this LOTUS, as we thought about it in Zipper, will probably move towards a new facility right next door to be right adjacent again. The first kind of experiment that wants to come in there, right, is Southern Power, along with their partner with TerraPower, Core Power, and EPRI, molten chloride reactor experiment. So that is what we're engaged with and aligned with to get LOTUS up and running so they can bring in that experiment and test it. Other things we do, moving away from test beds, is having some experimental infrastructure that we put in place to support developers and their R&D needs. Helium component test facility was completed in 2022. We've established some creep frames just as recently as last year, which are actually in the sample preparation laboratory, another facility very close to the dome. Metal, the Mechanisms Engineering Test Lab. This is an area where we're partnered with Argonne National Lab in Chicago, and they do sodium component testing in the metal. But it's NRIC infrastructure and supported at Argonne. And then Mystic, molten salt thermophysical examination. Kelly, this is all molten salt testing. And this is a picture, a little old too. If I took a picture today, right above these windows, there's 8 manipulators. You can actually see the holes here where they would go. So this is a shielded cell with manipulators. And then on the back of this is a glove box. So depending on what they're working on. So this is all for molten salt experiments. Virtual test bed. So I mentioned, I think on the earlier slide, that one of the other things we have is a virtual test bed, right? Where people can come and do modeling and simulation. Maybe it's industry, maybe it's universities, et cetera. But this exists. There's models in there. There's a library of information. And we get a lot of use on the VTB side of things. And the thought there, right, is how do we go to accelerate licensing, DOE authorization process, and just mature design before we actually start to build. So that's a virtual test bed. Addressing costs and markets, and how do we engage there? The first thing is advanced construction technology. So we actually partnered with GE Vernova on this. And, the objective was to reduce costs and schedule time. And one of the things that we took on very early was to come up with, right here at the bottom, the diaphragm plate steel composite. And this replaces kind of forms and rebar and all the labor and things that go in place of that. So what we did is proved out a principle where these get fabricated. This DPSC gets fabricated, brought on site, welded together, concrete gets poured within it, and it stays in place. So huge labor costs. So we worked on that through last year, probably start of fiscal year 25, into the calendar year 24, where we were doing the testing of that, proving that principle. And it was successful, right? So when we look at some of the samples and the testing was done at Purdue, the next stage was to actually build this. And so there was going to be a phase 2 process. So phase 2 was going to demonstrate the 60-degree pie-shaped wall. So we're just going to do it, to some scale. And we're actually still talking with GE Vernova and the Department of Energy on that phase 2 testing. So we haven't moved forward on it yet, but we're still considering that and other options as we move this forward. But that's the intent. Another area we went after was nuclear quality assurance challenges. A lot of costs and things were driven by NQA and NQA1. And so we kicked this off with kind of a workshop that we held just over a year ago now, December of 24 in DC. And you can see a wide range of people attended this. It was vastly attended, from developers, EPCs, suppliers, code committee, NRC, DOE, EPRI, NEI attended this, and really looking at kind of a workshop brainstorming, right, of some areas to go after and what we could do to make sure that we were appropriately applying, NQA1. And so next steps on that, we're looking at a number of things. How do we review, optimize, and modernize the requirements? use risk-informed performance-based approaches, integrate commercial grade dedication. And we're doing that within like NRIC 2 and some of our construction projects, right? Where we don't necessarily have to spec NQA1, but we can spec or don't have to specify NQA1, but we spec the components, bring them in, and then do a commercial grade dedication on them rather than, and it kind of opens up our world of suppliers that we can kind of go out to. Digital engineering. I mean, this was another area. I mean, digital engineerings are used widely across other industries, but not so much on the nuclear side. And so we really wanted that kind of digital approach, right? And we talk about things like single source of truth, where everything ties back together. We talk about digital threads that tie all the different systems together. And so we've been pursuing that heavily and using it in some of our upcoming construction projects ourselves, right? One of the things that we're doing under that whole effort is to have a digital twin of the dome. So you got the dome, you can actually, have a mock-up of some reactor that comes in and see how it interfaces, et cetera. But it's a digital twin. And then integrating AI into the process. So a lot of time, a lot of effort into kind of whether it's going through the DOE authorization basis or the NRC, and how can AI, as it's impacting everything in our lives, also help us in this and being more cost effective. And so we're working that. We actually put a pilot in place here just last fall, where we created kind of a set of inputs for a high temperature gas reactor, and then had AI generate kind of one of the safety basis documents, one of the chapters for that, right? And then, of course, just like all AI tools, and people have to go back and review them and make sure the output's good. So we had a lot of success with that. One of the challenges that we ran into was just kind of the firewall between the government cloud and the AI tool itself. So we're kind of working through some of that. We think in the end, I mean, it's not unreasonable to anticipate that we could have a 30 to 50% decrease in time to develop and review safety documents, accelerate the entire authorization process and the deployment of some of these test beds, and then future application to the Nuclear Regulatory Commission too, and their reviews. Maritime. So one of the things we do in maritime as we look at other markets is we've put together kind of from NRIC the Maritime Nuclear Applications Group, and there's 4 primary groups that we put together that focus on different areas of maritime and try to bring these entities together. I mean, it's a research hub, a resource center, we use words like that brings together all these different entities, for maritime applications. And the 4 groups are kind of shown here in the graphic. There's a public acceptance group, an R&D group, financial group, and then a regulatory group. And then a broad brush of participants. I think we talk here 190 members representing over 80 different companies that are interested in maritime. We put out a number of reports where we were part of a funding opportunity that ABS received, and we put out a number of reports here on maritime. Those are all available through kind of the NRIC website and a link to maritime. Ongoing efforts that we have, we worked together. I think the president last fall talked about a US-UK maritime corridor. So we're working with the Department of Energy to kind of lead that effort. We're extending to oil and gas and what may be some of the opportunities that we have there. looking at reactor technology suitability, so different vessels, different reactor types, that type of thing. Ports, what would port needs be? How could maybe micros or small modulars help the ports? And then, interestingly, final bullet, kind of a maritime nuclear language guide. One thing we ran into is there are some words that are used differently between, what would be considered maritime and what nuclear used. And an easy example of that most people can see is vessel, right? We talk about a maritime vessel. That's different than maybe a reactor vessel. So we've kind of put together a language guide that at least doesn't reconcile those terms because they are what they are, but at least lets us know that there are differences in the terms. A couple of other things I just wanted to hit on a little bit. So two entities, Oklo and Allo. I kind of have a slide on both of them. They're both siting here at the Idaho National Laboratory. Oklo, it says here, I mean, both of them are going through a DOE authorization program. They're both in the pilot program. I'll hit on that a little bit in a minute. They've both gone through groundbreakings last fall. And Oklo's goal is operational in 2028. So, and they're right on track for that. We help out through NRIC. I mean, it's not an NRIC activity, but we have program managers that actually are kind of the point and interface between Oklo and the laboratory where they're building on the lab itself. There's a lot of interface that has to happen there. And then we also help as directed by Oklo with some of the DOE, maybe it's engineering, maybe it's license or authorization, that type of thing. The other thing we're doing with Oklo is we're taking a facility that's kind of in that same fenced area where I talked about the dome was, the Lotus was, et cetera. And we are kind of turning that into a fuel fab facility. So they'll be constructing Oklo fuel at this facility. And this is a picture of it right here. It's called the Aurora Fuel Fabrication Facility, or A3F as it's often called. So we're doing both of those things with Oklo. And then Allo is building also on the INL a little bit. If I've mentioned a little bit, I don't have a map of the fenced area where the dome and the Lotus is. They're building right next to that fence, but on the outside. And they're making great progress with them. We interface much the same with them, right? They're a separate company. They're not funded through NRIC or anything like that, but we have program managers here within the lab that help them interface and support them wherever we can. They're actually looking for a dry criticality here by the July 4th deadline. And right now they're making fantastic progress in supporting that. So that's AlloX. The pilot program in general, most people are probably aware of that. Department of Energy reactor pilot program. 10 companies actually were awarded under that pilot program. Oklo had 2 different awards, so there's 11 total. And they're in that program. All of those companies, I believe, are going through like a DOE authorization process, which is one of the things the pilot program did them. And we're engaged heavily in some, but at least somewhat, and I believe all of them at this point. There may be some we're still finalizing some contracting with, but we engage heavily with this. And then, of course, the DOE other pilot program was the fuel line program. And that is what I have for kind of the slides, but I'm happy to take any questions and answer what I can.
I found I have this set up for my headset, so it doesn't work if I don't have my headset on. Yeah, thank you for that presentation. And yeah, I encourage the crowd here to go ahead and drop questions into the chat if they have some, but I will go ahead and kick us off. I've got a couple questions for you. Um, just getting down into the weeds a little bit, if you could just talk a little bit about the distinction between DOE authorized reactors and NRC licensed reactors, like that's not always clear. And like, how does the safety and oversight work for projects that go through NREC? Can you share that?
You bet. Well, I'm certainly not the expert on that, and there's probably people on the call that are, but generally the DOE authorization is through the local DOE office here. I mean, they're the ones that actually authorize the operation of that reactor. Vice, going through a licensing process that many commercial type reactors would have to go through. Typically, that DOE authorization is a expedited process compared to what it could be under licensing, although I think those dynamics are hopefully changing a little bit. But one of the things the pilot program did is extended that ability for DOE to authorize these test reactors, where normally they would, and some of them had already started going into the NRC licensing process itself. I mean, that's really the distinction of it. Once they actually go and they get past the test reactor stage that they're doing, maybe it's Oklo here on site or Allo or something, and they go out commercial, then they'll transition to kind of the NRC licensing. And the thought is that having worked through the DOE authorization process, they'll have a much expedited process through DOE I'm sorry, through the NRC licensing. So
Okay. And I'm also kind of curious, obviously some of these advanced reactor designs are going to be testing there. Are they required to go through NRIC to kind of reach commercialization, or is it just kind of one of several pathways? How does that work?
yeah, I'm really glad you asked that. No, there's absolutely no requirement on any level, right? We truly exist to help them through the process where it makes sense. And and that varies with every development. So, for example, I mean, Radiant is bringing their test reactor into the dome to operate. So we've established that capability, not just for them, but for them and others like them that want that infrastructure to test in. We also engage with them, as an example, on the engineering and nuclear safety, the authorization type work that we have. Other entities like the Oklos and Allos are building on site. We're engaged with them, but at different levels where we can add value and help their process. They essentially contract with us to do that. They could do everything on their own if they chose. We've seen companies that started off on their own, and then as they start working through maybe the authorization process, they've engaged with us based on our expertise and our history with the Department of Energy in working through those processes, and we've been able to help them that way. So it's not an all or nothing. There's certainly companies that there'll probably be a nothing approach to where they'll operate solely outside of our assistance, and not just NRIC, but the Idaho National Lab. And there's none that are all in on us, right? They're all doing a lot of their own work, but so just different levels of engagement.
Mm-hmm. And like you mentioned, like, for example, I think you mentioned Radiant's using triso fuel, is that right? And then you mentioned that Oklo, the fuel is going to be fabricated on site there. Are you
Yeah.
guys working? Because there's a lot of different fuel types too, right? Like, are you helping procure and design and fabricate the fuel? And how do you envision the long-term plan for fuel supply?
Yeah. So yeah, I mean, even with those that are using, HALEU, people have their own fuel spec. And so we're engaged with some. Um, but not all. We've had some of the fuel fab contracts that developers have ran through us to the actual fuel developer line. Maybe it's a BWXT or something. Some go direct. We're doing experiments on fuel itself. Maybe they'll design an experiment, run it through the advanced test reactor. We'll do PIE on it as they start, long-term fuel development plans. So again, different levels of engagement depending on what the needs are.
Mm-hmm. And just from a funding standpoint, are there's funding available. So like one of the benefits of working through NREC is that there is opportunities to compete for funding to work in the dome, for example. Is that right? So that how does
Yeah.
that work? Or are they bringing a lot of their own private funding to the table and investment as well?
Yeah, well, we don't fund, any of their reactor-specific tests or efforts, right?
Mm-hmm.
What we through the Department of Energy have funded the build out of some of these facilities, like the dome, that they can now come and use. It becomes a DOE asset. Once those developers come into the dome, they're funding their own tests, they're funding the operations associated with their tests. So we don't supplement that necessarily at that level. We have done some funding opportunities with them, though, where front end engineering and then some of the more detailed engineering, we've gone out with kind of a notice of opportunity. Hey, there's some funding available that the government's willing to put up to help you through these processes. And we've got another one. We called those feed front end engineering, experiment design, and detailed engineering and experiment planning. Those both had several entities in them that competed and were awarded some amount of funds. We're now got another kind of opportunity that we'll be putting out hopefully in the springtime here for some more engineering type support funds. So we help in different ways like that, but I guess it's important to note that in no way do we actually fund the reactor test itself, right? That's privately funded. And when a company like Oklo, for example, contracts with us, we put a contract in place and they pay us directly. They don't pay through NREC.
And so is that just kind of on a first come, first serve sort of basis in terms of how you're negotiating timelines and space for these companies?
So as far as supporting the companies, right? We try to do all we can. We certainly have some amount of limited resources, engineering type resources that can support them, nuke safety resources. Maybe it's first come, first served. We actually try to continue to hire and bring in more resources to support everybody. When we went out to test in the dome, like I said, Radiant's going to be the first one that's scheduled in the dome. We went out with a application, and we had 6 or 8 different entities actually submit applications to test and their timelines to do so. Went through kind of a review committee, and we awarded time in the dome on purely a scheduling basis. So that was competitively sought.
Okay. I'm curious too, like, are you seeing, we actually brought a group of Alaskans down there and we had an opportunity to tour NREC. I think it was almost 3 years ago now. And I know that was incredibly helpful. It was a lot of policymakers for the most part, a few folks from the utility industry and state government. And having the opportunity to really hear from the scientists, see where these systems are going to be tested. I've heard over and over again, like how important it was to that group to get to kind of see that on the ground. That was really useful. And so I'm kind of curious, you must be getting a lot of requests for visits and groups and stuff like that, and that sort of public education mission is so important if we're really going to see this next generation of nuclear technologies really come to fruition and the way that it may be able to do as part of our overall energy portfolio in this country. How are you balancing like the need to stick with your primary mission, but also creating this opportunity space for folks to learn about these advanced reactor designs?
Yeah, you're spot on. I mean, we get a very vast range of different tours that come through. Everything maybe on the government side. The Secretary of Energy was here last month. I think it was last month. Now times flies. To local groups, might be city groups, other developers, industry partners. I mean, there's just the array of people that come in and tour is extensive. I'm not aware that we turn down too many tours. I mean, we have a tour group and an office that can set those up if anybody's interested. But getting the message out, educating people, showing them what's here, that type of thing is tremendously important to us, and we support it 100%. And it doesn't interfere necessarily in kind of the primary mission of making the facilities up and running. But yeah, it's a big part of what we have to do.
Well, I do really want to thank the lab, Idaho National Lab, specifically, in terms of all of the support that you've provided in general to Alaska, in terms of just explaining the technology and answering questions just as a whole. So you guys have always been really terrific in terms of being available. Let's see, we do, one question, this came up yesterday too. This is from Nathan Green with at Matanuska Electric Association, so one of the utilities here in the state. A lot of people have this question, and it would be maybe great to get this out there again about these more naval reactor technologies, which are also sort of small reactor designs, right? That we have a lot of experience with as a country, and then these advanced reactors, microreactors, right? Modular reactor designs. So the question specifically is, can you talk about why we might not just be able to use existing approved naval reactors that are being manufactured now, such as the Bechtel A1B pressurized PWR that's installed on the new Ford class Air Force aircraft carrier? So do you mind commenting on that? I don't put you on the spot a little bit with that one.
No, I'm happy to, but again, I know there's probably science staff that could probably go into huge depth
Yes.
on this, right? But I mean it's different. I mean these micros that we're typically working with day to day are advanced reactors, right? So they're not your typical LWR PWRs or something that might be on the Navy side. They're also, of course, much smaller. I mean, they're the microreactors, small modular reactors. There's a lot of benefits to the advanced reactors from the safety aspects and things like that, and why this is being pushed. Yeah, so I think they're very different applications. Now at the lab, we are working not so much that I'm aware of with the Navy on some of their things, but for other things, right? Department of Defense, space programs, that type of thing, where some of these other applications are more suitable. And maybe that's what it comes down to a lot is, what's the suitability of the reactor type to the application? And that's where I see some of the difference. Again, I'm sure there's others that could provide a much better response.
Right. And my understanding is too that the fuel that the Navy's using, it's just like much more highly enriched. Those reactors are inherently not having those like intrinsic like safety, those passive safety sort of features that we're trying to build into these Generation 4 reactor designs. So they're not really.
Yeah, completely different fuel, completely different designs, still extremely safe, but some of the inherent safety features that you get in the advanced reactors would be different. So.
Yeah. To what extent are you working with other testing facilities internationally, like Chalk River in Canada or over in Europe? Is there much cross-pollination?
We've had other organizations from, say Europe come over and tour and see what we're doing. Um, Maybe Canada. I mean, when we were working with GE Vernova, I mean, they had an application, right, that they wanted to take out. And one of the reasons they were working on that advanced construction technology initiative with us was to apply that to some of the builds that they have going forward. Um, we're working that US UK maritime corridor. That was something that we were looking, how do you put some type of a vessel in place driven by nuclear and go kind of coast to coast on it. So that's right in its incipiency, though. So we just barely got started with that last fall.
So take us like a few years out into the future, like let's say 5 or 10 years. Like where do you see the trajectory going at NREC? Like what do you expect to happen? I know you laid out a timeline already, but a little bit more just kind of high level. Like what is your ideal scenario for where NREC is fitting in with the deployment of these systems on a commercial basis too? What do you think is going to happen?
Yeah, so I mean, there's a huge amount of momentum right now, right? I mean, there's a lot of startups out there and other companies that have gone beyond that. We're supporting them. We hope to see. I mean, when we schedule the dome out, I mean, the dome is busy. I mean,
Mhm.
it's you could say it's overprescribed. As we try to fit everybody into that and doing their tests. Hopefully, what happens with those microreactors and these developers is we help them do those tests, and then they can go out, demonstrate, and deploy, right? And that's really what we're here to do, is to help them make the next step, right? Whatever that looks like.
All right.
So it's all about
Well,
getting deployment in the
great.
so
Well, I mean, gosh, through your career too, you've just seen this like whole evolution. It's pretty interesting, I think. I'm sure for you this must be a pretty exciting time.
it really is, because 1987, when I kind of started at INL, I mean, EBR2 was an operating reactor and I was in operations there, right? And so now here we are re-establishing that to test these advanced reactors. So that's really neat to see that come around. So it's been fun.
Well, it is pretty neat, and since we're going to be hearing from Oklo next, like I actually think it isn't like the EPR isn't the Oklo Aurora reactor in some ways sort of the natural sort of
It is.
descendant of the
Yep.
EPRB2 reactor.
Yep.
Yeah.
It is. Yep. Fuel type and coolant. So yeah, no, I'm sure they'll talk more about it, but that's exactly right.
Right. All right. Well, thank you so much. I really appreciate your time. I am hoping to get down there with a group of Alaskans sometime soon again, and so we'll be coordinating with John and others at the lab. So hopefully we'll meet in person at some point in time in the future, Adrian. So thank you for your time.
You bet. Take care and thanks for
All
having.
right. All right. Thanks. So, Brian, I see you have joined us. So, you guys have been pretty busy lately. So, thank you. We haven't had a chance to meet in person, but certainly we are no strangers to Oklo, and we are really looking forward to getting an update from you. Uh, Brian, you are leading the business development at Oklo, which is a company that has had a pretty long history of engagement here in Alaska. I will let you talk a little bit more about it, but my understanding is that, gosh, I'm just trying to look that you've got a couple of decades of experience. I think I'm just going to let you introduce yourself, and including building and leading multiple organizations. So, Brian, you've got a presentation for us, and then we can do some Q&A afterwards. Does that sound good?
Sounds perfect. Thanks, Gwen.
All
Appreciate the
right,
opportunity.
fantastic.
Excellent. Well, really appreciate the opportunity to share a little bit about what Oklo is doing and provide an update on the Eielson project. We're super excited about Alaska and everything that's happening in the space in general. And as Gwen mentioned, I lead business development at Oklo. I've worked my entire career in the energy industry, not necessarily in nuclear, but on all different types of energy technologies, mostly on commercialization efforts. And working with utilities and how do you scale community scale programs. And today, I am really excited to share a bunch of updates and developments because so much is happening. It's almost a full-time job just to keep track of everything that's going on in advanced nuclear power right now. And in terms of the agenda for my talk, we're going to start with just a little background in history and an overview for because I'm imagining not everyone is fully up to speed on all the details of Oklo. And then I want to talk about all the recent developments, specifically as it relates to regulatory, because regulatory and licensing is obviously an incredibly important gate for us to navigate to be able to deploy and scale commercially. We'll talk about fuel supply strategy, because that's also another core bottleneck that we are in the process of overcoming. I'm going to go into the details of our business model and how we're going to market and how it is unique and different from some of the other companies and traditionally has been done in the space. And then most importantly, we're going to give an update on what is happening at IELTS now, what are the kind of key milestones that we're knocking down and how this is all progressing and moving forward. And then we're certainly going to have time at the end for questions and answers. And so that's what I'm planning to tackle today with the time that we have allotted. So I'm excited to jump in. And please, as we go, if there's any questions you have, just kind of jot down your questions so we can make sure to capture that near the end of the session. I want to start with just our mission. What is Oklo's mission? Is ultimately to provide really scalable, clean, reliable, and affordable energy. And we are very laser focused on the US market is our initial entry point in terms of our go-to-market strategy. But ultimately, we do plan to be a global company, and we get tremendous amount of inbound from all over the world in Europe and Asia, et cetera. But right now, we are laser focused on execution in the US is our first and foremost priority. And one of the things that I think is useful for us to talk about when we talk about Oklo's approach and is really to talk about the foundation of pillars that we're building on. And I like to frame this in the context of problems. Like what is the problem that Oklo set out to solve when we started the company or I wasn't here, but when the founders started the company in 2013. And I think there's really three foundational problems that Oklo is resolving. First is the massive upfront costs, the massive amount of capital that's required traditionally to build a more conventional large-scale light water reactor. Those plants are amazing. They've been kind of the backbone of our grid. We're incredibly big fans of large nuclear power plants. I think we should build lots of them. But the reality is that they take a tremendous amount of capital, and that is a very large barrier for many customers, especially, and they're not even an appropriate product or technology for a military base or a smaller utility or a data center. It's really designed, those traditional light water reactor plants, the 1,000 megawatt units, were really designed with large scale utilities in mind. But they cost about $10 billion. So it's a lot of upfront capital. So that's the first problem, is that high cost threshold. The second problem is build time. And build time of those large units are, you're talking about 8 to 10 years. And that's well beyond the time horizon of many customers' planning horizon, whether you're talking about data centers or even a military base or other potential customers. And then the third is public perception. There's some outdated information in the public, and I would characterize as misguided information just around safety and waste. And so when we think about those three things, I'm going to map those to Oklo's foundational pillars because what we're solving for is each one of those in a very specific way. So first and foremost, business model. So why is Oklo doing a power as a service business model? It is to knock down and solve that problem of high upfront costs. If you are a very large investor-owned utility, maybe you could put your balance sheet to work to fund something of $8 to $10 billion, but most customers are not. And so having a business model that enables power as a service to be able to pay as you go effectively is a real game changer in the nuclear power industry, because that is just not how the industry has worked traditionally for the bulk of its entire history. It's a reactor vendor, like someone like an Oklo, would have licensed their design to the utility, and then the utility would build, own, and operate that plant. So Oklo, we design, build, and operate our own plants, and our business model is power as a service. So that is one of the foundational pillars to solve that first problem of high upfront cost. The second aspect I want to hit on is size. And so we're building much smaller power plants, everything from all the way down, like in the case of Eielson, you're talking about a plant that's 5 megawatts electric and then balance it with thermal steam for district heating. And then all the way up to 75 megawatts for kind of our standard offering for data centers and things of that nature. But even in that spectrum of 5 to 75, that is tremendously different than a 1,000 megawatt reactor. And we're going to talk a lot about why that is and what are the economies of volume to get to scale and other benefits of having the redundancy, et cetera. So size is a big solution to build time, because instead of a mega infrastructure project that takes 8 to 10 years, we can construct these. I'm not talking about the total delivery, but construct them in 18 months. So that is a very different reality in terms of overcoming that speed to market and build time problem, which is problem number two, is that long build time. And then the technology itself is number one, it's a proven technology that has over 400 years of operational history around the world. We draw our legacy from what was mentioned in the prior session, experimental breeder reactor 2, EBR2, and that ran for 30 years in Idaho at Idaho National Lab. And what's really amazing about this technology is the inherent safety characteristics. One, so it really deals with this public perception problem around safety and accidents, because these are effectively self-cooling automatically that don't require backup power, don't require humans to do anything, or don't require pumps or mechanical systems. And then this technology also operates in what's called a fast spectrum and enables us to use recycled fuel. So we solve this public perception problem around waste. So when you talk about with the three problems I highlighted in the beginning, high upfront costs, long build time, and public perception around accidents and waste, you can see how the foundational pillars of Oklo, being business model, our size, and our technology, are designed to solve each one of those problems. So I think it's useful just to lay that foundation, because a lot of what I'm going to talk about today will become clear based upon the problems that we're actually looking to solve. So as I alluded to, we started in 2013. We are relatively still a small company. We're only approximately 250 employees, although we are growing incredibly fast. If you go to our website, and if you are interested in, we would encourage anyone that has relevant skills to apply. I think we have close to 100 open job positions right now. We're hiring very fast as we move into this execution phase. And the company went public in 2024. We originally raised just over $300 million and have since had follow-on additional equity raises of, this is even now out of date, multiple billions of dollars. So we are in a very strong financial position as we move into this execution phase to implement the vision that Jake and Carolyn, the founders, started in 2013. A few things that we're going to talk about today and I've hit on a few of these, but I just want to kind of comprehensively highlight the rest. We're going to talk about technology and size, as I alluded to, in the benefits of leveraging this legacy technology. We'll drill into the business model a little bit more, and most importantly, talk about how technology and size and the business model actually influence the economics. What are the unit economics of how do you build and operate these plants? And how these decisions around technology and business model and the size impact what customers we can even offer this to. Because historically, really, utilities were the only customer in the past, whereas now we're talking about military bases like Eielson, the Air Force. We're talking about data center customers, industrial sites, smaller utilities. There's a whole new cohort of diverse customers that, because of these technology, size, and business model decisions, we're able to open up this solution for. We're going to definitely drill into the regulatory path and how we've created a really scalable path. So it's not just a one-off, just checking the box and getting through once, but how we set a foundation to go through and ultimately have hundreds of projects get approved and licensed. And then what is our ultimate market position around execution and how all these things come together into a cohesive strategy that is really going to allow us to avail ourselves to all of the various financial incentives that are out there, as well as have a really well-capitalized balance sheet to go and execute. So all of these themes are going to kind of get woven together as we talk about the project and Oklo's approach. So what we're actually delivering is just a small power plant, right? I mean, what we're talking about is something that can be constructed in about 18 months or 1.5 years. We're talking about a size in the Eielson case of 5 megawatts electric plus the thermal steam that we're going to be providing, all the way up to about 75 megawatts electric. Because so in that range is the product that we're offering the market right now, which is a very distinct and different product, as I alluded to earlier. These power plants, each one of them sits on a very, very small footprint. We're talking about something as small as 4 acres. Now, this does not include a substation and parking lots and all of that. I'm just talking about the footprint of the power plant, the nuclear island, the balancer plant, the air-cooled condensers, and the core infrastructure that is required. So when you think about this as Lego blocks, if we're like a lot of our data center customers, they're looking at 500 megawatts or 1,000 megawatts or even more. You just put these in Lego-like fashion on a site, and it allows you to incrementally build out because each power plant is its own independent system. There's no dependencies of, let's say, cooling water or anything like that that is shared amongst these power plants. And the design life is 40 years. Now, we are also getting a license for our plants for 40 years. However, these licenses can get extended, just as all the large plants are now, many of them are going for NRC, Nuclear Regulatory Commission extensions happening right now. We can as well, and you can update and refurbish and replace different components of the plant. So it can go longer, but the design life is approximately 40 years for the product. So I just wanted to level set on what we call a powerhouse or Aurora powerhouse is just a small power plant that is independent in nature and then can be scaled in Lego-like fashion on a site. The product benefits of this. We hit on the simple and small design. Simplicity, I mean, we all know this just from it's kind of common sense, but the more simplistic a design, the more cost effective it's going to be. We all know that in anything in life, anytime you add a lot of complexity and a lot of detailed engineered systems that have layers and layers of redundancy in them, you're going to inflate costs. And so having a really elegant design that's simplistic with fewer moving parts and fewer things to go wrong is a huge advantage from a cost standpoint and just a maintenance and operation standpoint. We wanted to select proven technology. So a metal-cooled fast reactor were developed in the early 1950s. As I mentioned before, there's over 400 years of operational history running these around the world. About 25 of them have been constructed, and there's some in operation today in Russia and in China, and soon to be in the US as we start commercializing and deploying these. Cost is really essential, and we're going to talk a lot about that on how do we get to economies of scale through volume versus size. And we'll hit on that because looking for cost engineering opportunities to keep this to be competitive is incredibly important. And ultimately, providing this 24/7 clean baseload product, right? And, as we're talking about other energy sources that are more intermittent or less reliable, this is really solving for that problem, which in a military base like Eielson is essential that you have reliable, resilient, and affordable baseload power. And we have to have the safety, right? All of these inherent safety characteristics that we're going to talk about are really, really key. So all of these are the inherent benefits. So when we're talking about Oklo's powerhouse is a lot of people think about the reactor. Now, the reactor is just one component of the power plant. It's an important component, but at the end of the day, all it is a heat source. It's just a fancy way to boil water, right, and create steam, although a very important part of the system. And when we're talking about Oklo's fast fission reactors, if you could just imagine for a minute, just a large stainless steel tank, right? That these are non-pressurized tanks. These are not forged. This is rolled steel, 304 stainless steel. These are very similar tanks that are made in petrochemical and pharmaceutical other industries. So there's nothing there's no exotic materials used in making this tank. It is basically kind of existing supply chain, non-exotic materials. And that's really important. As I mentioned, can build a range of sizes all the way down in the Eielson case from a 5 megawatt all the way up to 75 megawatt. And obviously the size of the vessel can change, but ultimately we're trying to standardize as much as possible. And you can kind of ramp power up and down based upon other factors like the flow rate of the coolant and how much heat you're pulling off of this. So there's a range of power output that is possible. We operate at atmospheric pressure. So these are non-pressurized vessels, which really helps on a number of factors. Number one, safety. So if there were to be any kind of event or problem, you don't have any driving forces because it's a non-pressurized vessel. It also helps tremendously with cost because these vessels, there's about, for example, 20 domestic vendors that can make this vessel versus some of our competitors have very large, bespoke, pressurized vessels that have to be forged. And there's only one forge big enough in the world in South Korea and Doosan that can make those. So it's really important when you talk about driving competitive dynamics and reducing cost. It's just common sense that you want to have a competitive landscape of contract manufacturers that can make something. And we've identified 20 that our exact size, our max size and dimensions, they have shops domestically that can make these things at scale. And this enables us even geographically, depending where the project is, to contract manufacture with a shop to make a vessel, for example, that's closer to the project site. So there's a lot of advantages to that. And it just, again, it's about simplicity in the design, less things that could potentially go wrong if it's at atmospheric pressure. And we are operating at 450 degrees C, which gives for high thermal efficiency of these units and compared to the traditional light water reactor units that operate at lower temperatures overall. So these are just some of the characteristics of the reactor itself. But as I mentioned, the reactor is an important piece, but it's obviously just a part of a more comprehensive system. But as you see, this isn't an overly complex system. We in essence have the reactor vessel, which is the heat source, that is basically where nuclear fission is happening. That whole reactor vessel is full of liquid metal. So just imagine this big stainless steel tank, and the bottom of the tank, you have your fuel, and then the whole tank is full of liquid metal. So as that fuel heats up, as nuclear fission starts, it's transferring the heat to all that liquid metal, and we're pumping that liquid metal up through some heat exchangers. And all of that is, at the end of the day, again, it's like a big fancy tea kettle. You're just trying to boil water to create steam. And so you have a series of heat exchangers that basically, after you generate that heat, you transfer the heat from the liquid metal through a heat exchanger to water. And the purpose of that is to boil the water to create steam. And ultimately, you're going to turn a turbine. And at the end of that, you have all this heat you need to condense back. So we have air-cooled condensers. This is really important because now we don't need to be near water. We don't need an ocean, a lake, a reservoir. So it opens up siting possibilities tremendously because we're using air-cooled mechanism for dealing with that decay, excess heat out of the system. So those are the basic components of Oklo's design. One of the other benefits of having smaller reactor sizes is it's much easier to get to the level of reliability and resilience that's required of a military base or a data center, or those of a small utility even. And because Imagine if you have a large 1,000 megawatt reactor, well, those things are refueled every 18 to 24 months. What happens when you take it down for refueling? Well, where are you going to replace all that power? But when you have a much smaller unit, it's much easier to get to the level of redundancy of backup so that in certain applications, you can have multiple powerhouses on the site. So anytime you're taking it down for refueling or minor or major maintenance outages, you have that spare capacity that you can fill in the gap. And that enables us to get to this greater than 99% reliability that is often required by defense and data center applications. When we talk about nuclear energy, it's not lost on anyone in this audience, but it is really the cleanest and most environmentally superior form of energy we know as humans how to make. It certainly beats out wind and solar on the land use and materials intensity, and it even beats out wind and solar on greenhouse gas emissions. But I think when we think about environmental impact, the most important thing to keep in mind is land, water, and waste, right? You're basically wanting to look across these different dimensions, and all of these really nuclear is superior because it has the smallest materials intensity, meaning it's going to use the smallest amount of land, use the smallest amount of materials, and therefore create the smallest amount of waste at the end of the day out of this. And we'll talk more about the waste and any objections to that in a few minutes. But from an environmental lens, it's certainly the most superior way to generate energy that we've figured out so far. Let's dig into regulatory. So Oklo has been formally engaged with the Nuclear Regulatory Commission since 2016. And we've been putting in lots of iterative reps and negotiations with them over all this time. And finally, the light is at the end of the tunnel. And we are very confident based upon, at this point, over 600 technical and planning meetings. This is basically our engineers sitting down with their engineers and hashing out all of these negotiated details around workforce and operator requirements and security and environmental review and all of these different aspects. And we've submitted nearly 60 topical reports. These are basically white papers on each of these different topics. And so we've made tremendous headway in traction in this arena, and we're incredibly well positioned and confident of navigating this and having a scalable path forward. So much so that we've already started to break ground in construction on our first plant in Idaho. So in September, we broke ground, and as of right now, Kiewit, who is the lead constructor on that project, is basically blasting basalt. There's a bunch of basalt rock that is needed to be removed to where we're going to basically place the power plant. And so we can bore down for where the reactor vessel is going to sit. And that is happening as we speak. Right now, Kiewit is on site, blasting, doing site prep, and getting that construction process going. So there's a lot of activity and headway on that. And all of this leads into, well, even if you can get the thing licensed and you can start building it, if you don't have a fuel supply strategy, you can't turn that on. And to be quite frank, that has been the number one gating factor for advanced nuclear and SMRs in general, is having access to fuel supply. Oklo has a three-pronged strategy on this. So first is government supplied fuel. The US government is sitting on very large stockpiles of material, as evidenced, like our first plant that we're building in Idaho is leveraging the same fuel that was in EBR2, that experimental breeder reactor 2 that ran from 1964 to 1994. We are taking that fuel and recycling that for use in this first powerhouse that we're deploying. But there's also very large stockpiles of plutonium and other high enriched material that can be down blended and turned into 24/7 clean energy. And for anyone that's concerned when they hear the word plutonium, if you're really concerned about plutonium, the best way to truly get rid of it is to fission it. Basically, is to burn it. Right now, this wasn't being used for any other purpose. We as taxpayers were actually going to spend billions of dollars just to mix that used waste material with inert materials and just bury it, which ultimately, if you really want to get rid of it permanently, the best way is to fission it. So that material is available. the government is making it available. The administration's executive orders that were in May 23rd of last year has set this all in motion. And since then, Oklo has been awarded a fuel line, which enables us the ability to fabricate and work with that material. And we're in commercial negotiations with them right now to access that material. And we already have access to EBR2 fuel. So then there's fresh fuel. This is partnerships with existing enrichment companies such as Centrus, Hexium, Urenco, and others that enables the scale up of the supply chain for that fuel. And we're signing take or pay contracts that, because of the commercial agreements that we've signed, for example, with Meta recently, and our relationships with the government as well, are enabling that. And then the federal government has come in recently with very large awards to local enrichment of nearly $3 billion to help stand up the fresh fuel supply chain. So that's the second stream of potential fuel. And then the third is recycled fuel. So it is, many people characterize as nuclear waste. We don't believe that that's an appropriate term, because most what people are calling nuclear waste, which there's about 96,000 metric tons of it in the US right now, sounds like a lot, but when you understand it's really heavy, all of that nuclear used fuel that basically, from the last 70 years of commercial operation of approximately 100 reactors around the country producing 20% of our electricity, could sit in one Walmart supercenter. So think about that. All the waste from the last 70 years could fit in one Walmart. But there's so much energy still in that material that we want to harness and leverage. And Oklo announced late last year that we're building the first commercial fuel recycling facility in Oak Ridge, Tennessee. So $1.68 billion initial investment. And we are going through licensing and permitting of that site as we speak. And we're planning to turn that on in the early 2030s. So these are gives us three options for fuel sources. The government fuel is going to enable the bridge, right? That's going to enable us to scale faster, because that material, all it has to be is down blended. You don't have to do this very complicated manufacturing process. You're just down blending it and mixing it with uranium, fabricating it into fuel, and you can load it into our advanced reactors. Fresh fuel is incredibly important because we got to stand up the supply chain, and then the longer term strategy is recycled fuel. So all of that is underway and will meet different short, mid, and long-term needs. As I mentioned earlier, the business model is really, really important, especially as we talk about smaller utilities or military bases or data centers, because they are not going to want to come up with the upfront capital. And so by selling power, not power plants, is really foundational to, number one, come up with a very fast to market approach that is going to meet customers where they're at and what problem we can actually solve for them. And we're doing that through long-term power purchase agreements. I'll talk about the Eielson project in a second, but typically those agreements are 20 years. So the customer is basically saying, hey, we're going to buy X amount of power over a 20-year period of time at this cost and agreed upon price. And that is kind of how we're commercially constructing it. Then we take that agreement and we go to the capital markets and we finance against that to get the power plant built, and the combination of debt and equity. And we're able to leverage investment tax credits from the federal government. In some cases, up to 50% of the cost can be come back in an investment tax credit. We're able to access, and we're working with the Energy Dominance Financing Program of DOE, which would enable us to access low cost of capital in terms of the financing rate. And all of this gets into our ability to sell affordable, low-cost power. I mentioned the vertical integration of what Oklo is doing versus traditional. I think this slide illustrates that well. Whereas in the past, a reactor designer would just license their design to utility, and then utility would go and build and operate and get a license to operate that plant. Well, by vertically integrating, we can streamline this process. We still are working with constructors, so we're working with Kiewit in Idaho and Haskell in Alaska for the Eielson project. But ultimately, we're taking over many of the roles that the utility traditionally had done. And this really enables us to kind of streamline our approach for a regulatory process, we can go through in one step versus historically that has been two steps and just have a much more efficient process going forward. We built a very large pipeline of opportunities, both working with Department of Defense as well as Meta and Switch and other data center operators. And we don't need to talk much about this today, but this pipeline is almost growing by the week. And it's just incredible the amount of demand that there is for this product right now. So these are some of the partnerships that we've developed across the various supply chain in terms of powerhouse support. And we'll talk about, because we're going to go right into Eielson now, Haskell, which is our EPC that we selected for that project. We're working with Siemens Energy on our entire balance of plant. And you can see some of our other fuel supply chain partners and customers here. So let's talk about an update on Eielson and what it is and where we're at in the project. So first and foremost, the whole purpose, the mission of this is to provide very resilient on-site energy solution for Eielson Air Force Base. The base cannot fulfill its mission unless it has reliable, affordable, resilient energy. And so energy security and having this long duration islanded operation option is really critical to fulfill that mission. So our scope for this is all full stack, basically design, license, finance, construct, own, operate, maintain, and ultimately at the end of life decommission. All of that is within Oklo's scope for the project. This project, the way it's currently scoped, is a small amount of electric power, which is 5 megawatt electric base load. And then there's also a thermal component to this for district heating for the base, the 400 to 500,000 pounds per hour of steam that would help with that use case. In terms of auxiliary services for this, we would be providing metering and cybersecurity. This would be integrated within the combined heat and power and whole base distribution system. And this particular agreement is a power purchase agreement ultimately that will be for 30 years. Again, we can extend that. The design life of the plant is 40 years, but the initial power agreement, the way it was structured, envisioned, is for 30 years. And so where do we stand? Well, we have a partnership with Haskell, who is the EPC on this project. They have extensive experience on this base as well as just in Alaska generally. And we're very excited to work with them. They have a lot of core expertise just in power generation and working in Alaska and combined heat and power systems of this type, and specifically working in these Arctic and subarctic construction conditions. So the preferred site is near Spruce Lake. And then some of the key dates, just to highlight here, one of the things was, where's it going to be? There was a bunch of sites that were identified and that those have been narrowed down. And having that now selected is the preferred site, is what is this image showing on the screen. There's a number of studies that are happening that the Air Force is taking the lead on, the cultural and natural resources studies that are looking to be complete by midpoint this year in the summer. There's geotechnical work that is going to be happening this year that by late September, we're looking to wrap up. And then we are in active engaged communication with the Air Force around negotiating the commercial agreement and the lease negotiation and securing fuel and a bunch of commercial components that are ongoing as we speak. And all this obviously has to have things like the final site layout and environmental impact statement and things like that. So the environmental impact statement is going to take a little longer. But this kind of gives you some of the key milestones that we're doing in the near term, midterm, and a little bit longer term in terms of where we stand on the project today. So I know I've put a lot of information out there, and I know we're somewhat limited time, but I want to make sure we had at least 10 minutes I believe we have 10 minutes, correct? Or close to it?
Yeah, and we can go into the break just a little bit here too, so I'm not too concerned. We do have a lot of questions for you.
Okay.
I just want to just really quickly, so I'm just going to go through, and I've been kind of trying to curate these questions a little bit, but just super quick. You got the notice of intent to award last summer. So, and you're talking about like continuing to negotiate for the, the lease and the contract, the commercial contract. Like, what is the process for that? Like when, because right now I'm always just saying you have a notice of intent to award, but like, when will the contract be fully awarded? When can we call that an
Yeah, I mean,
awarded
I
contract?
don't have an exact date for you because
Okay.
we're right in the middle, like where there's weekly engagement, I can say. And this week even, our founders are meeting with folks from the Air Force and having these discussions around the commercial aspects of the agreement. So it's active right now.
Okay.
But
Okay.
until
Okay.
that process is concluded, it's hard to give you a specific date.
Sure. Okay. Yeah, understood. So just a few quick questions. Like you're talking about a 40-year sort of expected design life. Does that take into account refueling? Like what sort of timeline would you look at refueling the
Oh,
reactor?
so refueling happens on an ongoing basis, and so our standard reactor design operates on 6-year refueling for the entire core, but we actually replace a third of the core every 2 years. It's actually a similar cycle to the large light water fleet in the U.S. that every 2 years, approximately, depending on the plant, there's some variability, but you're looking at approximately every 2 years, you're basically refueling, in our case, a third of the core. So after 6 years total, you kind of work through. I always think of it as almost like a campfire, and you take your logs on the outside and you put them on the inside and put new fresh logs on the outside, similar to that, where you're taking certain assemblies out that are more burned up and putting new assemblies in, and they're kind of rotating through. But yes, there is ongoing refueling happening throughout that duration of time.
Does that require any kind of a substantial shutdown?
Yes, and that is partial. So we're always looking at providing an integrated solution and looking at other supportive technologies, whether we're including things like some grid power our gas generation, or battery energy storage, or other solutions. It's all site dependent of what is the integral best solution. But when you have to refuel, you're going to shut down, that is not a minor process. It's going to take approximately a month. So
Uh-huh.
it's substantial.
Okay. Okay, that's what I was wondering. And the size of the Aurora reactor has changed pretty significantly. I mean, it used to be just a handful of megawatts, and now we're at 75 megawatts for the INL project, but then we're still at 5 megawatts electric power plus some thermal output for Eielson. Is what's driving that? Is it technological or is it kind of a market-driven shift?
I would say it's market driven in the sense that, as everyone knows, there's been a huge kind of surge in demand from the data center industry. And I think a big part of the evolution of our product and going to larger sizes is to meet that demand. And what is the ideal increment of capacity that you can deploy? It's like the Goldilocks zone, right? You can have too small, too big, and just right. We're trying to get that just right for that market. And so, as of now, at least, we feel that somewhere around that 75 megawatt mark is the right increment of the right Lego block to be building. Because think of this from a cost and unit economic standpoint. One of the core theses of Oklo is that you want to take a lot of that low productivity construction labor that is used in these mega infrastructure projects and pull that into a high productivity factory environment. So you can get economies of scale through volume and quality control and just less labor and less dependency on delays of all these trades stepping over each other. And so to do that, you have to be able to not do a bunch of site welding. You want to take all of that into a highly controlled factory environment. And therefore, that's gonna constrain your size, because factories basically, to ship, let's say, the big tank, the reactor vessel, well, if you're over, let's say, 23 feet, you've number one, you've just triggered a very expensive and time intensive process of shipping this around. Also, there's not a lot of contract manufacturing shops that you can work with because it's too big if you go too much bigger than that. So if you think about this from a scalability and cost perspective, keeping something that's easily shippable, that's factory produced, that's replicable as a standardized product is very important in terms of logistics and cost and being able to get to scale in terms of volume. So all of those factors go into it. But the core of your question is it's market based in terms of the size of the demand that's out there and what product we're proposing to solve that problem, and also the cost. The larger there is economies of scale. I mean, the reason why we build 1,000 megawatt reactors in the country is because there is an economies of scale to going bigger. But it's a Goldilocks zone because if you get too big, you trip into a mega infrastructure project where all that concrete and steel and low productivity construction labor, and that's where we've been the Achilles heel of the industry. So we're trying to hit the sweet spot right in the middle. We can have all the efficiency of building, producing volume in a factory without the complexity and the site and inefficiency of site building.
So does that mean that the Eielson reactor in effect is like essentially already obsolete before we've even started constructing it?
No, not at all, because there's the military applications are going to need a smaller size. I mean, those are different use cases. A data center and a military base are completely different use cases. And Oklo is providing solutions for both. We're working across industry verticals. We're working with industrial customers like large chemical manufacturing companies and industrial sites. We're working with military bases. We're working with data centers. These are each separate and distinct use cases, and they require a slightly different solution. So in no way is it obsolete. I think it's very much the Allison project is a very important use case strategically for Oklo. We have to have solutions for military bases and to maintain the national security and ensure the mission of keeping that security in the U.S.
So you're kind of calling them both the Aurora reactors. So is there a significant technical difference between a 5 megawatt and a 75 megawatt reactor, or is it other than just the scale? Is it just a scaled up version?
It's a scaled up version. The core technology is the same. They're both sodium fast reactors. They're both doing air cooled. Um, for the heat sink, we're both, I mean, it's just you're going to have a different size turbine on there, and some of the components might have to be different size, but it's the same core technology that we're building. It's not different.
It's physically larger?
Oh, sure. I mean, it's going to be like a physical, the overall footprint won't necessarily be significantly different, but the size of some of the components would be different. Sure. Like the size of the steam turbine is likely going to be different for a 75 megawatt plant versus a smaller plant.
So for Eielson, part of the contractual arrangement is that you're providing both electricity and steam for heat to the military base. In that case, can you talk about like, is that something that you would be looking at for other applications, or like, and how does that affect project economics, like providing heat in addition to power?
Yeah, there are definitely a lot of industrial use cases for heat. Many manufacturing industrial processes require high temperature steam. That's one of the benefits of this design is we do produce very high temperature steam. I mean, we're talking about temperatures over 400 degrees Celsius. So it really opens up a lot of industrial opportunities and use cases. So it's not just for district heating for a military base. I think it's an important use case. And we're even considering this for cooling data centers counterintuitively because you can take high temperature steam to drive absorption chillers to actually cool a data center. So there's many applications for high temperature steam. So in essence, we have two products. We have steam and power. Those are the two products that we're delivering, and there's many use cases for both.
So what I'm understanding is that right now this 75 megawatt reactor design is sort of you talked about it as like a Lego building block for like your more commercial, like oriented towards server farms or things like that. Is that correct?
Well, I would say they're all
Yeah.
Lego blocks. I mean, when you buy a
Okay.
Lego set, you have different size blocks. You don't have one block. When you buy a Lego set and you're building a castle, you don't have one block that's the same. You have different size Lego blocks, and you piece them together depending on what you're building. And the same applies here.
Okay. So you have this agreement that's been in the news recently with Meta to develop like a 1.2 gigawatt advanced nuclear energy campus, I think, in Southern Ohio. So what would that look like in terms of putting these blocks together?
Those will be 75 megawatt powerhouses, and those will be built in phases. And that's one of the key advantages of that size. because even the largest customers in the world, the Metas and the Googles and the Amazons of the world that are building these mega campuses of gigawatt scale, they don't turn it all on at once. They build individual buildings that are between 100 and 200 megawatt buildings, and they're even phasing the ramp of those buildings in terms of the power use. So they're not turning on a gigawatt overnight. And so this enables us to scale the power infrastructure with the digital infrastructure in synchronized fashion. So you can coordinate the build up. You don't want to overbuild your power infrastructure and have it sitting there be uneconomical because it's not right sized for the application. So the 75 megawatt powerhouse is really perfect for the data center industry because now you can coordinate the build out of these large master plan campuses.
So even at 75, I'm sorry, I'm like hung up on this. I'm just curious, like that 75 megawatt threshold, that's not really a technical limit. That's sort of the right size Lego block for the most having the most flexibility for these commercial applications. Is that sort of what it
I
is?
would say yes, there's two parts of it. So one, yes, just commercially and from a market perspective, we feel that that is the in that size range is the perfect kind of Lego block to build out these master plan campuses. And then second, as I mentioned before, the size really has to do with cost and unit economics. Once you start getting into larger reactor sizes of, let's say, into hundreds of megawatts, you start tripping into territory of a mega infrastructure project. And that has been the Achilles heel of the industry. All the schedule delays and cost overruns around the massive amount of civil works, the concrete and the steel in these mega infrastructure projects with thousands of people, trades tripping over each other and dependencies. We want to alleviate that problem. And so having a factory produced product at volume is part of the way we accomplish that. So there's two parts to your answer. One is we think that this is the most economical size that maximizes the amount of energy per unit that you can ship effectively and produce in a factory. And it happens to be the right size for the largest load that is starting to dominate the grid in terms of the increase in power demand right now. So it's both those things.
And so, I mean, I'm curious, like, has there been any discussion or would it be possible to think about upgrading the Eielson reactor from 5 megawatts to 75 megawatt reactor design if there was a customer for the additional power?
Certainly, those are part of the commercial discussions. I mean, we have to also follow. There's a procurement process that was done formally that we have to honor that process and that approach. I think from Oklo's perspective, we have a lot of flexibility in the way we're thinking about approaching it. We want the best solution for Eielson, right? At the end of the day, that's going to be most cost effective and meet the mission and intent. And so we're working through those details right now with Air Force to figure out what is that optimal commercial agreement and how that would be shaped.
And so I'm just going to ask one more question, and there are a few more in the chat if you have time to maybe look those over and maybe drop some answers in. But I'm interested in your business model, this power as a service sort of approach to things, which I think seems really forward thinking and smart. I'm curious, do you envision those as like sort of fixed price contracts, or would those be tied to, other alternative fuels like natural gas or something like that?
Well, they would not be tied to alternative fuels like natural gas, but there is different ways to construct this commercially, and it really depends on the customer and the use case and what is optimal. So we have flexibility. For example, you can, and we will likely have fixed price contract. This is the price of power, whatever it is per kilowatt hour for 20 years or 15 years or whatever the duration of the contract is. Then there could be another model where you have, okay, there's an annual escalator. Here's the fixed cost, and here's the annual escalator that we're going to build in. Another model is you have your base cost, and then the fuel cost is variable, meaning the source of the fuel, and that can float. So there's different ways to construct it, and it really, at the end of the day, comes down to what the customer wants to sign up for and what risk or that they want to take on in kind of any variable costs regarding fuel. From our perspective, the unit economics of the fuel should decrease dramatically over time, especially as fuel recycling comes online, because we can decrease our fuel costs by up to 80% through multiple rounds of recycling. So there could be aligned incentives with us and a customer to have the fuel be variable within a PPA arrangement. But all of that, we have a lot of flexibility and creativity as we work with customers. Our intent is to have a very customer-centric solution that addresses their concerns and risks.
Thank you, Brian. I really appreciate it. This is fantastic information. I think we're always eager to hear from Oklo and get some updates on this project. So thank you for taking the time with us today. Like I said, if you've got any time, there are some additional questions in the chat. If any of them are ones that you could give a quick answer to, that would be great. Otherwise, we might even just reach out to you guys later and just see if we can get a couple more answers. I know folks are pretty excited about what you guys are doing. So thank you for your time today.
Thank you. Really appreciate the opportunity.
Okay, and we're going to go into a short break. It's just going to be 7 minutes right now because we want to come back and talk a little bit about the economics, maybe kind of riffing off of Brian's business model that he mentioned here with Idaho National Lab. So thank you, Brian, and I hope to keep in touch. Hello there. Welcome back. All right. I hope everyone enjoyed that quick break. I now have the pleasure of inviting and introducing Hayden Bryan to join us. We actually have 2 speakers from Idaho National Lab. They're going to be speaking about the economics of advanced reactor technologies. We're first going to hear from Hayden and then from Dr. Boutros Hanna. Hayden Bryan is a nuclear energy economist at Idaho National Laboratory, where he focuses on the economics, deployment readiness, and regional impacts of advanced nuclear technologies, including small modular reactors and microreactors. I had a little bit of a chance to get to know Hayden, and he's done some interesting analyses for Alaska. Maybe we'll get to hear about some of those, but most recently he worked on a high-level assessment of options for nuclear energy within Alaska's Railbelt, and I asked him to join us today to speak a little bit about that. So Hayden, I'm going to go ahead and turn it over to you. I think we have about 15 minutes, then we'll hear from Boutros, and then we'll go to some Q&A. Does that sound good?
Thank you again for having me. Yeah, I'll keep this to 15 minutes. There's a lot to talk about in Alaska, a lot to talk about in the Railbelt region. So definitely more than can be talked about, even just in 2 days, as we can tell from the fact that this is a conference, a multi-part conference. So this talk that I'm giving today is based on a paper that INL put out, which was responding to a request from Senator Geisel, which was based off of a recognition that Alaska is facing significant energy challenges, but there are also significant energy opportunities in the state. This is in recognition that nuclear energy is a secure, reliable energy source, and it does not require constant refueling, as opposed to some of the energy technologies currently utilized in the state. So with the recognition of those benefits of nuclear power, the senator requested that Idaho National Laboratory study the near-term nuclear energy deployments along the Railbelt corridor and look for some specific sites in the area for nuclear deployment, specifically of small modular and microreactors. The study scope, and these are some important caveats. So what the study was and what it did not do. We conducted some open-ended interviews with Alaskan energy experts and experts within the University of Alaska system. We did a site screening and high-level techno-economic framing and examination of current energy context, including grid constraints, fuel risk, and potential for non-electric applications. The caveats on what the study did not do are, in this case, almost as important as what we did do. We didn't make any siting decisions. We didn't do a vendor down select. We didn't say, yes, Oklo, no, Oklo, which I'm sure that Brian is happy to hear. We did not run any cost estimation exercises, and we didn't rule out or rule in any potential locations. What we did, though, is what you see at the top here is identify high potential opportunities, specific locations that stood out as these are likely first adopters for advanced nuclear technologies in the Railbelt that would help address key energy needs and spark economic development in the region. So first off, the high-level findings that we applied to high potential, these high potential opportunity sites, and these are based directly off of the interviews that we conducted. So the region faces transmission challenges and generation backup constraints. So the rail belt can be best thought of, and I know that I'm preaching to the choir here, but the rail belt can be best thought of as an interconnected network of microgrids. And there are limited backup generation within the region. And so any amount of stable, reliable baseload generation is kind of worth its weight in gold in the area. That is kind of doubled by the fact that there's the looming natural gas insecurity in the Cook Inlet. So the cost of recovering natural gas from the Cook Inlet is increasing as the resources in the inlet decrease. And there have also been a number of challenges with the suppliers moving out or potentially not continuing their contracts in the region. Third, there are a number of benefits of utilizing some of the existing infrastructure that we looked at. So these are coal, diesel plants that already exist in the region. And so we look at INL at a lot of coal to nuclear transitions or diesel to nuclear transitions. You can use the existing balance at plant, the existing transmission infrastructure to reduce the cost if you were to kind of replace the generation assets with a nuclear small modular reactor or microreactor. You can get significant cost reductions, as well as potentially increasing reliability and decarbonization. Fourth, in the region, there's a huge importance of heat. A lot of times heat generation can be as important as the electricity generation. And fifth, there's real identifiable suppressed demand in the region. So there's suppressed commercial demand, industrial demand, and residential demand. I'll get into that a little bit later when I talk about the overlaps between what nuclear can do and what's needed in the region. But sixth, seismic risk is taken seriously. It differs by geography. But that was a conversation that came up repeatedly in our discussions with the experts. And then finally, this is not a numbered item, but a bullet point, because we were looking at commercial applications of nuclear, not military applications, but there are, as discussed previously, military bases like Eielson that are seen as natural early adopters. They already have staff members. They have an extreme reliability need, and they don't like having a constant need for refueling. So they're a very natural early adopter for nuclear. As discussed previously, they're already looking at doing so. Again, kind of preaching to the choir here. These are things that are already known, but there are transmission and generation constraints in the rail belt. This is a look at those aspects, but there's a $400 million project with $200 million of cost share from DOE aiming to increase transmission from about 80 megawatts constraint to 250 megawatts. And any new generation capacity added creates momentum for new transmission infrastructure. A little bit more on the natural gas shortages. So Railbelt utilities remain dependent on natural gas extracted from the increasingly marginal and cost-intensive reservoirs in Cook Inlet. And the natural gas, so the two kind of main alternatives being discussed to resolve this issue are either import from elsewhere in the region or from other countries, and or a pipeline from the North Slope. Both of these are options, but they both, of course, introduce costs and complexity. regulatory complexity, and they have significant lead times. The challenges, of course, are already looming. And then third, both affordability and reliability could and perhaps already are being negatively impacted for both residents and businesses should regional natural gas production fall short of demand. So now we can move into the alignment of the Railbelt requirements and some of the benefits of advanced nuclear capabilities. I know that some of these were already covered in previous presentations, and this is kind of what the entire conference is about. So some of these I can move through quickly, but I think it's an important point for us to touch on. So the matched capacity between what the Railbelt needs and advanced nuclear. Traditional scale nuclear power plants are in the hundreds of megawatts up to gigawatts, whereas advanced reactors, small modular reactors, microreactors are as few as 1 megawatt up to tens of megawatts, or the small hundreds of megawatts. And that's really the size that's needed by the Railbelt. And the transmission capacity of the Railbelt as well. That also allows you to build your generation capacity incrementally as your load evolves and not take on too much financial risk. The fuel security as well. You're moving away from something with either diesel or natural gas that needs a constant supply chain and constant refueling to something that is refueled on the order of years as opposed to constant. Again, as I mentioned, the existing infrastructure, you can potentially reduce your costs by up to 10 to 35% if you utilize existing infrastructure. This picture on the left, this is Kemmerer plant in Wyoming. It's a coal to nuclear power transition that they're looking at. And then on the right, you can see the Beluga natural gas plant. That's actually one of the plants that ends up being one of the sites that's selected in our study. There's the suppressed demand. So mining is a large suppressed demand that ends up showing up. There's these energy intensive economic activities that are constrained by energy cost and availability. It represents demand that's operating below its economic potential, not speculative growth. This carbon neutral heat, there's district heating in the region, and that could be expanded. Nuclear cogeneration can supply reliable heat and electricity while reducing emissions. And then finally, nuclear is a very reliable technology, and that's a very beneficial capability to have in Alaska. Again, this also matches very well with military or critical infrastructure, which require uninterrupted power and heat. So then the study candidate sites, presented in no particular order, that came out of our conversations with the experts in the area. So the Aurora coal power plant, which is 27.5 megawatts electric. It has a district heating site that provides heat to around 200 customers. Customers doesn't mean people, that means buildings. And that turns nuclear heat into a primary product, not a byproduct. And it has very winter peaky load, and also air quality pressure makes coal replacement very politically legible. It's the cleanest example of a brownfield transition as opposed to a pure power swap. Beluga is a central Railbelt node where firm capacity has system-wide reliability value, and existing generation in the substation context favors drop-in nuclear replacement logic. The construction, given Beluga's location, is of course going to be a little bit harder than average if that is a site that is considered, but the operational value is unusually high there, given that it's a brownfield site and it's not being used. It's a mothballed site, 281 megawatts potentially there. Healy power plant, This is an important site because it sits at the hinge of the north-south Railbelt intertie. And it scales in value as transmission expands, even if it's constrained today. That's going back to the 400 million DOE cost shared transmission expansion in the region. So the coal to nuclear transition preserves the generation town's economic role. The North Pole power plant, this because it's naphtha and diesel, that changes the economics greatly. All of the natural gas, you could say, you're competing against very inexpensive natural gas. Here in North Pole, you're competing against diesel, which is a lot more expensive. So those comments don't come into play. So you're competing against an expensive, volatile price liquid fuel rather than cheap gas. And of course, when I say cheap gas, you have to think again about the challenges that are kind of looming, not to be bringing in doom and gloom, but the challenges that are occurring with the Cook Inlet natural gas resources. So North Pole, there's strong cost emissions and logistics risk reduction story there. And then finally, Seward. This isn't like the other cases. This isn't a brownfield swap out, but it's close to major fiber lines that reach the mainland US West Coast. So there's some opportunities for data centers there. So this is best framed as a staged microreactor proving ground, not an immediate baseload hub. That what were the results of our studies. Of course, there's a lot more that we can go into there, but that's as best as I could fit it into 15 minutes. And that exactly took me to 15 minutes on the second. So thank you so much.
Great job, Hayden. And I would just to ask you just before we go to Botros, like, did you wind up doing some pros and cons of these sites and like selecting like which ones shook out to be more optimal here?
Yeah, there's definitely pros and cons to each. Like I mentioned, North Pole.
Yeah.
There you're looking at replacing diesel, and diesel, of course, you're talking about, it's not just the price of diesel, it's the price of transporting that diesel, and it's the price variability of diesel. Aurora and Healy, it's not just coal, it's the transport of coal, but it's also all of the emissions associated with coal. Healy, it's the fact that it's the main interconnect between the north and the south, but there's also the transmission, the investment in the transmission infrastructure between the north and the south. So each of them have certainly their pros and the cons, but I think one of the most important points that came out of this work was investment anywhere investment in generation anywhere will increase the investment in transmission everywhere. And I think that's one of the biggest stories to come out of the work.
Okay. Yeah, great. Thank you. I have like about 10 other questions for you, but I'm going to actually hold them so we can.
I have about 10 other answers. But
yeah, good. I want to go ahead and switch over to Botros.
Thank you so much.
And yeah, if you want to go ahead and pull your slides up, let me see here. So Dr. Botros, you're actually a modeling and simulation nuclear engineer at INL, and you specialize in nuclear reactor techno-economics, computational fuel dynamics, AI, machine learning, and software development. So you're looking at the physics to economics optimization, and that's the tool that you've been working on developing for advanced reactors, which I think sounds really interesting. So I'm really glad that you had an opportunity to join us. So walk us through what you've figured out.
Yeah, thank you so much for having me. So today I will talk about some of the work that I did for the economics of microreactors. It's about economics of microreactors in general, maybe not specifically for Alaska, but I hope that some of the work and some of the results here will be interesting for people in Alaska as well. So this is just a general overview of nuclear reactors and what a microreactor look like compared to other nuclear reactor. In general, it has a small power, usually lower than 20 megawatt electric, and a smaller footprint. It is less than 1 acre, and it is designed to be passively safe. The nuclear microreactors are not a new idea. They have been used in the Army nuclear power program, and also they have been used for space reactors. Right now, people are interested again in nuclear reactors, also for military applications, for remote communities, for microgrids, for data centers, and so on. And you can see how microreactors look like compared to the human, and how this is different from small or larger reactors. The benefits of microreactors, why microreactors are attractive in general, because they have a small size and they should be easier to transport, especially to remote places and military bases. The design is simple and it is made to be fail-safe. Also, it can be built and connected relatively fast, within a few years. So it should be built faster than larger reactors. Also, it is designed to be more and more autonomous. It can be located with the end user. Um, and it's also a fast way to learn from real world operational data. You can build the reactor relatively fast, uh, and get a lot of operational experience compared to larger reactors. And also, as many people talked before, it's flexible to site because it can be transported. The challenges of microreactors, the first one is this economy of scale. So for microreactors in general, the cost per kilowatt or megawatt hour is relatively high compared to larger reactors. The second challenge is the fuel availability. So many of the microreactor vendors right now are interested in uh, different fuels compared to those that were used in large reactors. So we're talking about high enrichment fuel or HALO. We're talking about the TRISO fuel. So these are relatively new fuel that have limited supply chain. And another challenge in the regulation. So if we will talk about transportation, or operation that is relatively autonomous, there are some regulation challenges that come with that. Um, Again, just showing that there is a lot of excitement about microreactors. So you can see there are right now 36 projects of nuclear reactors in North America. 11 of them are microreactors. And when you talk about microreactors, you have all kinds of microreactors and several designs and technologies. And 18 of these projects are expected to be deployed by 2030. Um, so now I'll focus more on the economics. So just to give an idea what do you mean by the economy of scale, here I'm showing the the overnight cost of a microreactor, and the operational and maintenance cost of a microreactor. And you can see how the cost gets really higher for a small reactor. Just to give an example, if you have a large reactor like 1,000 megawatt, you can reach an overnight cost as low as $6,000 per megawatt. But if you are talking about a microreactor that's 1 megawatt, this overnight cost can be up to $18,000. The same for the operational and maintenance cost. For microreactors in general, the operation and maintenance cost is relatively low. It can be as low as $20 per megawatt hour, but for smaller reactors, it can be as high as 160, 180 dollar per megawatt hour. Of course, these numbers will be different from a design to another. This is just a plot showing numbers from different designs in the literature, just to give an idea um, about the diseconomy of scale. So, how to estimate the cost of nuclear microreactors? So there are already a lot of cost estimates of microreactors around for a while, but we thought it's important to develop a bottom-up cost estimate for microreactors as detailed as possible, and trying to look at designs that the industry is interested in, designs that use halo fuel, TRISO fuel. Also, we had the opportunity that uh, in INL we have the Marvel project, so that's a microactor project, and we got some cost data from that project. So this helps us to come up with a relatively realistic cost estimate of microreactors. If you are interested in the methodology in detail, how we came up with such a cost estimate for several microreactors, um, you can scan the QR code for the published report. You can also scan another QR code for a tool for cost estimation. This tool right now is a Python code, so we are working on a web-based app that can be used by more and more users. So what I'm showing here is the three reactors that we worked on estimating their cost. The first one is a liquid metal thermal microreactor. The second one is a gas-cooled microreactor. And the third one is a heat pipe microreactor. You can see that the gas-cooled microreactor and the heat pipe microreactor are fueled by the TRISO fuel. The liquid metal thermal microreactor was fueled by uranium zirconium hydride. The power range here is between 7 megawatt thermal and 20 megawatt thermal. The coolant is sodium potassium for the liquid metal, helium for the gas cooled reactor, and heat pipe for the heat pipe microreactors. And all of them have a relatively high enrichment, almost 20%, and they have several lifetime for the fuel. It's important to make some caveats here. The first one is that before I show the cost estimate for the reactors, it's important to emphasize that economics are not the only factor in making decisions about using or investing in a specific microreactor. There are several factors that we considered, like capacity factor, safety, operational experience, supply chain, thermal efficiency, and so on. So economics are one factor to consider, not the whole story. Also, the three designs that we considered here are just examples. I mean, there are a lot of variation of design of microreactors, and these designs are pre-conceptual. The reactor designs were not fully optimized, and the cost estimates were developed with incomplete information. So we made some assumptions to come up with these cost estimates, and these numbers should not be used for investment decisions. Okay, so all the numbers that I'm showing here are in 2024 USD. The cost includes the cost of pre-construction, something like licensing and plant studies. The direct cost, this includes civil work, reactor systems, fuel, and so on. The indirect cost, so this includes the engineering and project management, the training cost and financial cost, and the operation and maintenance cost. When you look at the three actors that we considered, you will see that the capital investment cost is not that different. It's between like 136, 153 millions. But when you look at the capital investment per kilowatt, it's significantly different. So it's $25 dollar per kilowatt for a liquid metal microreactor, $27 per kilowatt for a gas-cooled microreactor, $54 per kilowatt for the heat pipe microreactor. We added the cost of the operation and maintenance. we ended up with a cost of electricity to be the levelized cost of electricity, the LCOE, to be around $330 per megawatt hour for the liquid metal microreactor, uh, higher than this $400 uh, per megawatt hour for a gas-cooled microreactor, and higher than $900 per megawatt hour for a heat pipe microreactor. We also estimated the levelized cost of heat. So in general, we know that the overnight cost for heat application is like 20% less compared to electricity application, and the operation and maintenance cost is almost the same. So using this information, we estimated the levelized cost of heat to be around $87 for liquid metal microreactor, more than $140 per megawatt hour thermal for a gas cooled microreactor, and over $300 per megawatt hour thermal for heat pipe microreactor. So in general, you can see that the liquid metal microreactor has a significantly lower cost than the other two design. Uh, this has to do with the trisofuel. So the other reactors use trisofuel, which has a lot of advantages, but it's relatively expensive. Also, because when you use the trisofuel, it has a low fuel density, which means that you need more fuel and you need a bigger core and bigger reactor. This also makes the cost higher and higher. A heat pipe microreactor has the highest LCOE in the design that we investigated because it has a low power, only 7 megawatts thermal, and it has a low power density, and also again because of the high cost of the trisofuel. We also found that there are a lot of costs that are not sensitive to reactor design, like the pre-construction cost, the training cost, the staff of the operation and maintenance. All of these costs are not sensitive to the reactor design. Now, how can we reduce this cost from the first of kind to nth of a kind? The key factor here is the factory fabrication. So this slide shows some work that we did before with Monroe, which is a manufacturing company, to develop a model for a factory for microreactors. As you can see on the right side, uh, it's a factory with assembly line with different stations, and the more microreactors include, the cost will be cheaper. So this factory includes around 22 workstation and a final assembly line. The equipment cost was estimated to be 6 million if you are producing 10 reactors per year, and 10 millions if you're producing 100 reactors per year. The operating cost would be between 7 and 25 millions per year. And when you increase the number of reactors that the factory is producing per year from 1 to 10, the cost drop by 70%. If you increase it from 10 to 100 reactors per year, the cost drop by 50%. And of course, it's important to emphasize here that we're talking here only about the components that can be manufactured in a factory. Uh, for some activities and some components uh, have to be on site. For example, uh, the refueling or the startup, all these kinds of activities will be done on site, so they will not benefit from factory fabrication. So using some lessons we learned from the factory fabrication, we estimated the nth of a kind cost for several reactors. Um, you can see that when you look at the nth of a kind cost, the cost difference between the three reactor designs that we considered is not as significant as it was in the first of kind cost. For example, the levelized cost of energy for first of a kind liquid metal microreactor is 25% cheaper compared to a gas-cooled microreactor. But when you consider nth of a kind's cost, it's only 6% cheaper. And again, I'm emphasizing here again that levelized cost of energy is not everything. You should consider other factors like the supply chain, capacity factor, and other factors as well. So what are the cost drivers of microreactors? Here I'm showing the cost drivers of liquid metal thermal microreactors. The first one is the capital plant expenditure, which means how much cost, how much you are spending every year to replace some components of the reactor. Because if you are replacing the reactor vessel or the reflector or the drums every 10 years, 5 years, or something like that, this means you have to get several drums or several reactor vessels over the plant lifetime. The second factor is the reactor system. Also, the plant licensing um, is another cost driver. The energy conversion system, which is the turbine, is another cost driver, and of course, the fuel drives the cost as well. Similar cost drivers were found for the other designs, except that the contribution of the fuel becomes higher and higher when using the TRISO fuel. Now, to put costs in perspective, so are these costs high or low? We need to compare to something else. So here in this plot, um, okay, I talk about this figure, uh, using the publicly available data about the wholesale electricity, the annual average electricity prices are between 30 and $60 per megawatt hour. So based on these numbers and based on the results we have, microreactors cannot compete with the wholesale electricity. Now for the retail electricity, which is the customer, the prices that the customer receive, uh, the nuclear microreactors can compete. So you can see here in this figure that the nth of a kind microreactors can compete or can penetrate the market in 14 states. We're talking here about behind the meter arrangement, where the reactor and the user are co-located. And of course, microreactor will have a higher and higher a chance in penetrating the market when you talk about remote communities or military bases or mining sites. It's important to emphasize that this study did not consider the government incentives like the investment tax credit and production tax credit. These subsidies and these tax credit can effectively reduce the cost. Also, this study did not consider the impact of multiple units. So if you are building several units together, the LCOE for the LCOE will be reduced. This is another way to look at the cost and how the microreactors will penetrate the market more and more when you build more units. So for a first of a kind reactor, it might penetrate the market only in remote communities or maybe in defense application. But when build more and more reactors, they can be also useful in specific states that have higher electricity prices like Alaska. And according to the results we have so far, it's hard to expect that the microreactors will compete with the US grid. That's the end of presentation, and thank you for your time.
Great. Thank you. Thank you, Botros. That was terrific.
Thank you.
And I think we still have Hayden here too. You guys both available for some questions? All right, excellent. I'll just, Botros, just because you are finishing up, just a couple of super quick questions. Did you include decommissioning costs in
Yes.
your estimates? Okay.
Yes.
Where did you get the numbers from? Where were you basing these numbers off of?
Yeah, that's great. So obviously we don't know the decommissioning cost of microreactors, but there are some models that were based on uh, larger reactors. So we use this
Okay.
model to estimate the decommission cost.
Okay. And the same, like, so, what reactor lifetimes were you assuming for these? Did you make?
Right. So, I mean, reactor life, so we assumed, I think, like 40 or 60 years.
Oh, okay. Okay. So pretty significant.
Yeah.
Okay. Cool. All right. Well, I'm kind of curious. Like my first question to both of you would just be for Alaska in general, but let's just say the rail belt because Hayden was working. Let's start with the rail belt anyway. We can move on to other use applications. What do you guys see as like the next step? Like if there's interest from the utilities, what should we be doing up in Alaska while we're waiting for these to become a little closer to full commercialization? What can we be doing to get ready or to be thinking about this? Hayden, you did a very high level initial analysis. Like what are the next steps?
I've also done a number of projects in terms of public acceptance of nuclear, and I think that the United States, unfortunately, has a history of doing nuclear first and asking questions later, and that's a model that is not sustainable. And we now have an opportunity to do um, do a better job. And so having conversations with people first, saying that this actually is um, the best way to decarbonize, to have reliable, cheap energy, and it's safe. And to go in and have genuine conversations with people, allow them to ask hard questions. I think having those honest conversations with people early and often is the best thing to do. So things like this that we're doing now.
That's sort of like a little bit of like just kind of socializing, the idea with the public around this new generation of nuclear. And but maybe Boutros, I'll give you an opportunity to answer that question too, because I think that Alaskans are sort of eager to figure out, is this a technology that has real applications for us? And if so, how do we figure that out? Assuming that we kind of intersect with this nth of a kind, that the costs are coming down. Doesn't look like they're going to be that inexpensive, really, right? Like it looked to me like you're talking like 14 to 18 cents or something like that. Or I guess you had it in megawatt hours. I was thinking about it, 14 to 18 cents per kilowatt hour is kind of was that kind of what I was seeing that you were coming up with for an nth of a kind reactor?
Yeah, so that's the lowest value we have for an instance of a kind. It was 180, I think, dollar per megawatt hour. Yeah.
Okay. Yeah, and
Yeah.
that's not that inexpensive, right? So, we're not really talking about cheap power here. So, understanding exactly all the use cases, exactly where this would make sense, how do we get to what are the next steps that we can take to kind of get us to not necessarily a decision point, but a place where we can say, yes, this is still something to be looking at, or no, let's check this off the list. This doesn't really make sense for our particular application. What could we be doing?
Okay, that's a broad question. But I would say that, as Hayden said, what's really important is to ask hard questions for the vendor as much as possible about their supply chain, about um, the operation experience of different reactors, if they have a detailed cost estimate or not, if the project is mature enough or not. I think the more questions, the better. I mean, for example, nuclear energy in general is known to have a high capacity factor, above 90%. So you have a nuclear reactor that's available all the time. For advanced reactors, this can be a challenge. So how will they achieve a high capacity factor to make sure that reactor is uh, is available most of the time? Are they sure about their supply chain? This supply chain can be impacted by several things like pandemic and wars and all of that. So asking more questions will help in making in getting to the point where we can make a decision.
Well, that's actually kind of an interesting point. So, like, you're kind of talking about that sort of more one-on-one relationship with an individual vendor to look at a particular application. And that's something that's kind of interesting to me because one thing, my observation, and you guys can tell me if I'm wrong, but there's a lot of vendors in this market. And it looks like some of them are doing quite well. You know, you've seen others that have actually, for example, USNC was quite active up here in Alaska, and they've gone out of business, right? And so, how smart are we to like really get closely engaged with individual vendors versus like figuring out the optimal use case for us now, and then selecting a vendor as they're a little bit further along with their designing and early stage, testing to see what the optimal technology solution is for us a little further down, but having like really designed our optimal use case in the meantime.
I think that can be a yes and, or perhaps like a both sort of scenario. I mean, you can engage with the vendor and the technology. I think it's important to look at what technology is going to be the best fit, look at what capacity is going to be the best fit, and also look at the vendor and see, does this vendor check all the boxes to INL, we can't comment, and we're not in the business of picking favorites between vendors. So of course we're going to be very careful about how we answer this question. But there are some vendors that through this kind of economic down select will survive the process, and there are some that won't. And I think through that process of asking tough questions, you'll be able to suss out who's who. And that's why, I mean, Gwen, I was impressed with some of the questions that you were asking earlier in the panel, because that's the exact kind of questions that you need to, not you, Gwen, but I mean,
right.
Everybody needs to be asking
to Alaska. Yeah, that we all need to be asking. Yeah.
Because I think it's a yes and to find I mean, even like with what Boutros was presenting with the costs of microreactors, those are the costs of microreactors being compared to the cost of Railbelt electricity, and the microreactors themselves aren't necessarily specifically designed to meet Railbelt electricity.
Yeah.
They're even for a more niche, that's SMR territory. And so again, it's meeting the technology and the vendor specifically to the need, and asking those questions again.
Mm-hmm. I mean, one thing that I'm interested to hear from both of you is, if things go well, let's just say best case scenario, right? That we see a little bit of like fast tracking of some of this technology development. We're starting to see some of these early pilot projects. We're starting to see some first commercial projects. Do you perceive that there could be like a very big glut of like a big demand for these that really can't be met just because there's just really, limitations in how much vendors could even produce, right, to meet a certain demand? And so, you've got like sort of a niche market like Alaska might get a little bit iced out, right? That's a kind of a question I always wonder about. If we're not at sort of the front end, are we going to be looking at 10 years before, 10, 15 years, like before these other pent up demands are met, and we can really enter into this market? So I'm kind of curious what you guys think. Like, what do you view as the trajectory? Or Boutros, when you're looking at that like nth of a kind, how many reactors are you really assuming can get built by a vendor in a year? Because I don't think this isn't like a Ford assembly line, right? Like we're not talking about hundreds a year here. Like, what are we expecting production rates to achieve?
Yeah, so I think for this analysis in particular, when we're talking about nth of a kind, we're talking about 100 reactor. I know 100 reactors, 100, yes. I know that that's a lot of reactors, but
Yeah.
we need to have more demand, so the cost of different components and different materials go down. Right? It is Like if you have a fuel fabrication facility that is helping only one or three vendors, that's not as helping 100 vendors. The demand will increase. You have more, the capacity will increase. So uh, hopefully you'll have more competition and the price can go down. Um, so yeah, we estimate it to be 100 reactors in our study.
Like across a number of vendors or in total? Like because you have the three different categories, right, that you were reviewing?
Yeah, that's a great question, but I would say like at like 100 units for the same design or for the same component or for
Okay.
fuel. Yeah.
So for the heat pipe reactor, the one with TRISO fuel, were you modeling like the radiant system, the Kaleidos reactor? Is that what you were modeling, or was it a generic?
Yeah, it was a generic one. It was
Okay,
generic.
because I saw you had the picture of radiant in there. So
We don't have enough information from a specific vendor to.
yeah.
It's a simplified pre-conceptual generic heat pipe microreactor design. Yeah.
Okay. Was there some reason why you then, if it was a generic design that you had, that these different sizes, like 20 megawatts thermal for the liquid metal, 15 for the gas cold, and 7 for the heat pipe reactor? Why did you assume these different sizes?
Okay, that's a great question. So for the heat pipe microreactor, usually the capacity is low because it depends on heat pipes instead
Hmm.
of a pump or compressor. And usually the heat pipe technology has a limit on how much heat you can transfer. So if you check any heat pipe microreactor design online, usually they have a low power. At least that's my understanding.
Hmm.
I didn't see like SMR with a heat pipe technology. So usually they have a small power compared to the other reactors. For the gas cooled microreactor and the liquid metal microreactor, you can actually see that they almost have the same power output in terms of megawatt electric. So they
Hmm.
both have 6 megawatt electric, but the high temperature reactor are expected to have a higher thermal efficiency. That's why its thermal megawatt is higher.
Okay. And did you look at any applications for combined heat and power at all in terms of the economics? Because that could improve the economics, right? If you're able to use heat as well.
No, we didn't try to think of both heat and electricity combined. No, we didn't do that. But that's a very good point. Yeah,
Okay. I'm
specific
just
customer
curious
that
about
can
that.
be important. Yeah.
And
Other
oh, I'm sorry, go ahead.
other
Did-
studies at INL certainly have,
Mm.
though.
okay. Okay. Did you assume that the reactor, sorry, Botros, I guess this is to you again, would be base loaded? Is it just because when we were hearing from Oklo a little bit earlier, right, they were talking about the potential for some ramping. Like, did you just assume base load output?
Yes.
Okay.
Yeah.
So sort of like the optimal output from an efficiency standpoint for the reactor.
Not optimal. I would not say optimal. So just to give a perspective, so this work started by designing a tool for microreactors where you can change the power, change the fuel, and so on, and get different results. The result that I have shown for 20 megawatts thermal and so on. I just thought that this would be interesting and kind of representative but of course, I mean, the power can be higher or lower, and there are trade-offs that you will have when you do that.
So going back to so the nth of a kind concept there, when I was speaking with one of the vendors, they are anticipating, and I won't say which one it is, but they're really only anticipating building a handful each year. And this is a major vendor. This is a large vendor with real manufacturing capability. And that was surprising to me because, to me, like, what does nth of a kind actually mean? Does it mean unit number 100? Or are we talking unit number 8, right? There's a big difference there. And so I don't know, maybe because you're talking about like this idea of 100 a year or something like that. That seems like more than what I've been hearing from the vendors. And trust me, I could be wrong. So please correct me if I am. That we could expect anytime in the remote near future, you know. And so what are we kind of talking about in terms of you envisioning sort of ramping? Like what kind of assumptions did you make about getting to this nth of a kind designs?
Okay, that's a great question. So in general, first of all, just there are a lot of costs that are associated with the first of kind reactor. So just building the first of a kind one and starting to build the second or the third, there is a significant cost reduction that will happen because of that.
Mhm.
When I was talking about nth of a kind reactor and I said we assumed 100 units, this doesn't mean that 100 units per year in general, it just means that there is a demand of 100 units. So you are building the same thing again and again and again. It doesn't necessarily mean 100 units per year. In the factory fabrication slide, I just wanted to show that if when the market increases and there is more demand and there is more production, the cost significantly goes down. But even in that slide, you can see that from one reactor to 10 reactors, there is a significant cost reduction as well.
Okay. So Hayden, I want to go back to you. I think you've actually done a little bit of work even in Alaska, looking at some more remote applications like mining, for example. Is that right? You've looked at that?
Yeah, and I saw that there was a question from Chris, and I wanted to touch on some of the points about mining. So first off, on future proofing for future sites,
Mhm.
that's definitely a little bit out of my wheelhouse. But I'll say that in terms of future proofing for sites, you'll certainly want to think about some nuclear sites. You'll want to think about first off the security implications, and then the emergency planning zones. Certainly, the microreactor, small modular reactor emergency planning zones are smaller than traditional scale nuclear plants, some even as small as the site boundary. But just in terms of being thorough when you're going through those before you design. And then in terms of if you want to pull heat, the considerations. But there are certainly people at INL and other labs that we could put you in touch with. So I think that our email addresses will be made available and we can put you in touch with other people at INL. And then in terms of the other just interesting interrelationships between mining and nuclear in Alaska, first off, mining is a very high capacity factor and reliability need industry. And also, there's a lot of unique interrelationships between the native corporations and the mining corporations that can lead to some really unique financial interrelationships and economic impacts. So, for example, Red Dog Mine, I know that we're stepping outside of the Railbelt there, but Red Dog Mine and the Native Corporation have like a 50-50 cost share. And so if, for example, Red Dog Mine were to shift from using diesel to using a small modular reactor, and it were to reduce our cost, that could increase the mine lifetime, that could increase the cost share to the Native Corporation, that would increase the economic impact for the region, that could reduce out migration. There's kind of a high touch point on really salient issues for the region. And I think all of those things, I know that we're close on time. I could talk a lot more about that, but there's a lot of very interesting topics that you can go through in terms of mining and nuclear in Alaska.
Have you, it's interesting to me that you did that analysis related to Red Dog Mine, and I'm kind of curious, and I think even Graphite One as well, maybe.
Correct.
I'm sort of curious, what was the genesis of that? Because are you seeing kind of increased interest from the mining industry around nuclear? Is that sort of where that came from, or?
Those were not done at the behest of the
Yeah.
mining corporations. Those we actually used the data from the mining corporations. And again, this was saying these are likely first adopters. Those mines, for example, use, I'll just throw a number, 14 million gallons of diesel every single year. And you're talking about bringing it in on a barge. And if you're in Nome, that's one barge per year. And if you don't get that one barge in, perhaps you have to contract a Russian icebreaker vessel to get that barge in. And it becomes a little bit of a nightmare. And if it's graphite one, then if that mine comes into play, you're talking about a quadrupling of the amount of diesel throughput for Nome. And then you're also talking about a very high economic activity, like the amount of dollars coming through the mine, as opposed to the city, it's a huge disparity. And so then you have questions about, in case of a shortage, who gets diesel first? And those kinds of questions are just fascinating to me, and why when anytime a question about Alaska comes through kind of our hopper of research questions at INL, I try to jump on them. And so I've had a lot of opportunities at INL to research those, but also just in terms of economic impact analyses, a lot of times those can be really dry. There's something called leakage, where a lot of the economic impacts leave the region. But when you have these interrelationships between mining corporations, native corporations, that actually keeps a lot more of the impacts within the region than you would normally anticipate. And that, to me, makes the economic impact analysis a lot more interesting, because your leakage proportion decreases substantially.
Yeah, and I do know, I think we do have some folks from the mining industry were joined us yesterday. I'm not certain about today, but it is really an interesting use case in my mind. When I've spoken with some of them, what I hear is that, mining already has all these challenges around, various, different kinds of concerns around environmental contamination and, things like this, permitting. So like the idea of like taking one system or one, process that's already got all these challenges in terms of getting through a gauntlet of permitting and local support and all this, and then adding a second technology kind of layered on top of that has like a whole different set of, issues associated with it potentially, right? Feels kind of scary, like it could really hang stuff up. But then I do think that people often aren't thinking so much about like the contamination potential of our status quo, right? So we're talking about diesel fuel. We're used to shipping diesel fuel. We have a lot of spills associated with diesel fuel, but we sort of take that as like, okay, that's just part of, the reality of using fuel. It's more, typically like more diffuse pollution, right? Typically speaking. Not always, but usually. And so we don't really think about that so much as like, what are the possibility or the potential for environmental contamination associated with a microreactor compared to shipping in, you were saying like one, tanker full of fuel every year to Nome, something like this, right? And then if you're talking about graphite one, potentially trucking it to the site, or if you don't build transmission lines out there, I mean, there's a lot of complexity associated with that. So it'd be interesting to like really be looking at that as a use case. I'm actually kind of curious. On our next panel, we have someone from Saskatchewan, where they both do mining and are very interested in microreactors. So I'm kind of curious if they have any thoughts on where those two overlap a little bit. But I'm glad you had a chance to look at that. Yeah, go ahead. Absolutely.
If you're part of a large mining conglomerate that's decided to go carbon neutral by 2050, what other option do you really have for dispatchable power than nuclear? I mean, if there is one, let me know. My email will be sent out. But yeah, thank you so much. And also, please correct me if I've been wrong on anything, but I appreciate it. Thank you for having me.
No, I really appreciate both of you. The economics of this are really important. And it's nice to just have a really honest look at it, not just assuming, oh, this is going to be really cheap power, but really putting it in perspective, like where does it fit into our existing and future energy mix? So thanks to both of you. Really appreciate it. So,
Thank you.
Yes.
all right. And with that, we'll go into our last panel. This is what would it take? Community and utility reflections on nuclear energy. So we have 4 folks on the panel here. I'll just do a super quick introduction of all 4 of them, and then ask them to do a little bit of a self introduction, as well as a little bit of they're each going to speak a little bit on their perspectives and what they've worked on related to nuclear, and then we'll go into a little bit of a conversation. I'd love it if folks, drop any kind of questions that you have, even ones that might not necessarily be precisely relevant to this panel, and we can see if we can weave it in here, or we can try to get some of these answers to figure it out in the future, like through a working group meeting or another vehicle. So for this panel, I would like to first welcome Diane Hirschberg. She's the director of ICER, the Institute of Social and Economic Research at the University of Alaska, Anchorage, and she's a professor of education policy there as well, and a very close collaborator with us at ASAP. Travis Millian is the CEO and president of Golden Valley Electric Association. So Travis, I don't know how long you've joined us today, but there's a few questions that stacked up for you with relation to the Eielson reactor. But you've been the chief operating officer there since 2023. You're an electrical engineer with over 25 years of experience in the utility industry, and you have done a lot of interesting things in that time. Greg Pelter, thank you for joining us with the School of Environment and Sustainability. You're the co-lead of the Energy and Mineral Resources for Sustainable Future signature area at the University of Saskatchewan, and we have been working together quite a bit on nuclear, along with a lot of other energy technologies. But Saskatchewan's a place that's been doing a lot of very interesting work. And there's a lot of there's no active reactors there today, but they're very much exploring that potential for the future. And there's also Saskatchewan is one of the places globally that is very active in uranium mining. And so we did have a lot of questions related to mining. And so it's great to bring you in here, Greg. And then Phil White is Associate Professor of History and Arctic and Northern Studies at UAF, so one of my colleagues. He is an energy and environmental historian, and he recently completed a book chapter called Atomic Currents, the U.S. Military and Nuclear Energy in the Alaskan Pacific. And that was just recently published. So, all right. Well, thanks to each of you. So why don't we go ahead and start with you, Diane? Do you want to introduce yourself a little bit more?
Sure. As Gwen said, I am director of the Institute of Social and Economic Research, and I've been doing that for about 4 years, but I've been here at UAA for almost 23 years. And my work has evolved from being education policy focused very directly, but getting involved in rural and then Arctic education policy issues, and that morphing into broader interests on sustainable development in the Arctic. And of course, Arctic sustainability is highly dependent on energy. And Greg, who'll be talking shortly, really pulled me more directly into this field and got me collaborating with Gwen around a project to work with communities on how they define and want to move toward the right mix of energy for their own sustainability. And I think, that theme of what is it that communities themselves want and how are they themselves defining what sustainability is and what the right energy mix is. I mean, that's really critical. That's actually the same thing if I'm talking about education. What does it look like not to have a imposed colonial system, but a system that recognizes the knowledge and ways of sharing knowledge that are have been in existence for thousands of years in these communities. So we have been collectively working together on projects. And of course, the project I started with Greg and Gwen, the CASES Community Appropriate Sustainable Energy Security Project, was really focused on renewables. And as Gwen knows, I have a different history with nuclear that is more around nuclear, the proliferation of nuclear weapons, and perhaps a little bit of activism around that as an undergrad at Berkeley. And so when Gwen approached me about working on a project on nuclear energy, I was nervous and skeptical. This is a nuclear energy university project, but again, the question was not, is nuclear the right technology? The question is, what are community views about whether nuclear is the right technology? And at the same time, it was also, the beginning of my learning about what are these next generation reactors and how has this changed from the legacy that many of us in my generation have in our heads about Chernobyl and 3 Mile Island. And so I have evolved in how I think about nuclear energy. I still am a strong opponent of any nuclear weaponry, but I also am really clear that I am not promoting or opposing these technologies for any given community. I want to make sure that the people that are in the communities are making that decision first. I don't know if you wanted me to dig into anything else about that.
We can dig in a minute here. Why don't we go ahead to Travis first?
Great.
Yeah, thank you, Gwen. As Gwen mentioned, backgrounds in electrical engineering. I've been in kind of the utility space or utility engineering space for over 25 years now. Been in Alaska for just over 20 years. What started my career was working for a company called Schweitzer Engineering Laboratories that design and build protective relays for power systems. So that's where I first got introduced to the power utility space. Had an opportunity to move to Alaska, like I said, over 20 years ago to go work for the High Frequency Active Auroral Research Program, also known as HARP. Now, at the time, was an Air Force Research Labs facility that was co-sponsored by the Office of Naval Research, now is ran by the University of Alaska Fairbanks Geophysical Institute. Been involved with that project even after I left that project to go work for Copper Valley Electric based out of Glen Ellen. Was still involved helping out the university on power generation and managerial consulting type work. Worked at Copper Valley Electric for 12 years. Started as their power generation manager, moved into their chief operating officer position, and then spent my last 4 years as their chief executive officer. During that time, Gwen and I worked quite a bit together, working on some legislation in the state of Alaska, specifically on micromodular reactors, smaller than 50 megawatts for siting conditions. During that time as well, we spent about 2 years at Copper Valley Electric evaluating micromodular reactors for our service territory down there and looking at different optionalities and economics and what could or could not work. Unfortunately, which I'm sure we'll get into it a little bit more today, it didn't work out for a number of reasons, mostly on the economic side because you're competing with low-cost hydro energy down there, which made it very difficult to make it economical. Been now with Golden Valley for about 2.5 years, started up here as the COO and then assumed the chief executive officer position about 1.5 years ago. So based here now in Fairbanks, and we're still work with Gwen quite a bit on a number of different things, but happy to have the conversation today.
Great, thank you. Greg, do you want to introduce yourself?
Howdy. Yeah, thank you, Gwen. So as Gwen and Diane have mentioned already, I've been working with both of my Alaskan colleagues here at Grapes. It's over a decade now already, going back 2015. But I'm at the School of Environment and Sustainability at University of Saskatchewan. I lead our university signature area, co-lead with my colleague from chemistry on energy and mineral resources for a sustainable future. And outside my academic life, I was a negotiator for SAS Power, which is we have basically one electricity company in Saskatchewan, which is a government-owned, vertically integrated company with a fleet of a little over 5,000 megawatts. And so that's how I came into this bailiwick. It's on the nuclear file is all I think Gwen will ask me to talk about a little bit. There is very high interest. We don't, Gwen's quite right. We don't have an active operating nuclear power plant in Saskatchewan. We did have a research nuclear reactor, a slowpoke reactor for several decades on campus at the University of Saskatchewan. But our province will be adopting, and to Hayden's thing, when he said when you're going to coal, the other option is nukes. Well, he's right. So yeah, that's where we're going with 300 megawatts. We'll be bringing online probably within 10 years. They've already pretty much selected what they're going with. But the interesting story in Saskatchewan, which I'll talk about later, is on the front end of the whole fuel to energy cycle, and that's on the uranium mining side, in how that worked with the indigenous communities. But I'll just leave that for when we get to that part of the chat.
Okay, that sounds
And
good.
it's great to be chatting with Alaskans again. Hey, I miss you guys, all of you.
Bill.
Yeah, Gwen, thanks for that introduction. My name's Phil White, so I teach history here at the University of Alaska Fairbanks, and I'm an energy and environmental historian. The classes that I teach are focused on the history of Alaska, history of the circumpolar north. So I have the privilege of looking at other northern nations and their power systems and their various degrees of decarbonization over the decades. And my research has spanned a few different areas, but what originally brought me to Alaska, like many others, was the pipeline. But unlike those who physically labored on the pipeline, my labor has all been intellectual. And so I'm finishing a book on the environmental history of the pipeline right now, and that's led me down a bunch of different fascinating rabbit holes. I wrote a history of electrifying the Railbelt, Alaska's Railbelt, so I'm very familiar with the development of that power system, as well as another chapter on the state's electrical history. And as we all know, the history in rural Alaska is quite different than the history of the Railbelt, and that brings me to the work that Gwen mentioned. There was just recently a volume published about the history of the U.S. military, the environmental history of the U.S. military in the Pacific. And for that, I did a chapter about the history of nuclear power in what I call the Alaskan Pacific. And the reason I use that term is many other authors have focused on nuclear weapons testing, right? Amchitka, Project Chariot, and some of the fallout of those endeavors. But there has not actually been that much research and scholarship on nuclear power generation. And Diane, I really appreciated your story about your prior interactions with nuclear weapons, because so often those two things are conflated. And I think that is a legacy we are very much dealing with today because of how the federal government treated Alaska, honestly, as this nuclear testbed for a variety of technologies. Those legacies are still alive and well. And so I was fascinated by what I learned in this chapter, because on one hand, we have the history of Fort Greely, the SM-1A, which I know folks have talked about a fair amount throughout these various conferences. And I would put that in the category of nuclear testing that did not go according to plan and that has left some significant social and environmental legacies. And then on the other hand, we have a form of nuclear power generation that almost no one talks about in Alaska, and that's because it's been maritime. And that's the history of the nuclear navy in Alaska. And that history, by and large, has been one of phenomenal success. And so one of the key things, one of the key arguments I make is that this isn't a simple story of nuclear good or bad. It's really a question of how this technology gets deployed, right? And so I've learned a lot through that research and am fascinated by all aspects of energy in Alaska. And so have been greatly enjoying this conversation and look forward to jumping in and talking about it more. And then I should also say, beyond my work outside the university, I've worked for consumer advocates on various power issues on the Railbelt. So that has brought me into contact with a lot of folks who have, I would say, strong views against nuclear. So I'm very familiar with the kind of, I would say, typical environmentalist critique of nuclear power, which I don't exactly share, but I would be happy to talk. We can talk through some of those concerns as part of this discussion.
Yeah, I actually, that since you bring that up, maybe we can just go ahead and start there. And so, Diane, I'm going to bring this back to you and then to Phil. We'll leave Travis and Greg out of this for right now. But it is kind of interesting. There are one thing that I have observed, and I think Diane, you could speak to this a little bit, is that as folks like learn more about the technology and become more informed about it, they seem to typically have more positive perspectives of it. That's not entirely true, but there is sort of this, group, I'd say, of people. There's like in our polls, there's like 10% that are like never nuclear, right? Like no way, right? Not in my backyard anyway, right? And so I'm kind of curious, like what your thoughts are on the perspectives there. I think part of it is this idea that nuclear is competing against renewable energy, right? A lot of folks that are like very strong proponents of renewables. I think maybe all of you are falling. I don't know, but like, do you really see this as like a this or that choice? Like, is it a bifurcated choice? Like, if we do microreactors or nuclear or these advanced reactors, that means we're going to be doing less renewables. Do you see them as complementing each other? And from that environmental perspective, where we're concerned about, climate change, about emissions and things like this, like, do we need to take another look at nuclear? Because frankly, there are not that many other alternatives for baseload energy. So I guess I'll just Diane, do you want to start? And then I'm kind of curious, because I think both of you have been pretty active in environmental spaces in the past or now. So yeah.
Absolutely. And I'm going to circle back, sort of bounce a little bit off of what Phil was saying, because, in the work that we were doing with our Nuclear Energy University project, so we'll call it NEUP or NEUP, what we were hearing in a lot of places is less. There's a lot of people who don't understand the new technology, but that's not where the biggest pushback came from, particularly in the communities that are closer to where Project Chariot was happening. It was fundamental distrust.
You might want to explain. I don't know that everyone, maybe talk about what Project Chariot was in a nutshell, since both you and Phil have mentioned it now. Not necessarily everybody here is familiar with it.
So everybody go read Firecracker Boys. But Project Chariot was an effort to develop peaceful uses of, it was part of a broader U.S. effort to develop peaceful uses of nuclear technology. And the proposal on the table was to detonate a bomb underground that would create a deep water harbor in Northwest Alaska. And obviously that didn't happen. But what did happen were a number of tests to see what does it look like in terms of dispersal of radioactive materials on the tundra, or when they were digging core holes and using diesel fuel. And there was, when this work was discovered and halted, there was people were told that it was cleaned up, and it really hadn't been cleaned up to the extent that people had been told. And I'd say there's a long legacy of incorrect information, but not just incorrect information. Really, improper is a nice way to say handling of communications, and just a complete failure to do due diligence to understand the communities in Alaska, so that even when we, many years later, asked for a briefing from people who'd been involved with the remediation cleanup of that area, they had the names of the tribes wrong on the materials that they posted on a federal website. So it's deeper than just we didn't clean this up well enough. It's really something that has created a lot of distrust. And frankly, the news story that came out this morning from NPR about secret changes to regulations around environmental standards for nuclear, that is simply going to reinforce that distrust from people who may be open to learning and changing their mind about the technology itself, but will likely be much happier to talk to Oklo than to talk to somebody in the federal government about nuclear. And I think that's I think that becomes part of our challenge in this. Is not only do we need to talk about the difference between nuclear weaponry and nuclear energy, but we also have to talk about the difference between federal government decision making and how the decisions are made, and what the private sector and local communities are advocating for and deciding about.
Bill?
Yeah, there's a lot to say here. So, Diane, I appreciate that history of Project Chariot, and this was part of a broader plan to create what was called a panatomic canal, a new Panama Canal using nuclear explosives across the Isthmus of Panama, Project Plowshare. And so, Diane's absolutely right. I mean, the fallout from this project is alive and well with us today, because it didn't end when the project ended in the 1960s. There was that discovery of those nuclear materials in the 1990s. And so people remember this, right? As a historian, I can say this very well. And then there was other concerns over, the Air Force's deployment of RTGs, right? I'm going to get the acronym messed up here. But the devices that were deployed in rural Alaska that did not use fission to produce power, but the heat from the material. And so I think what we see here is what happens in the past is still very much alive and well with us today. And that's not only from a community perspective, that's also from an environmental perspective. I think you also hear from a lot of folks who there's certainly a lot of truth in this, say that, nuclear power has always been a militarized technology. And they feel that it is, fundamentally associated with militarism to pursue this technology. And of course, that is a feature of its historical development that wasn't inevitable, but that is how the technology grew and emerged, and probably grew and emerged a lot faster than it would have otherwise without the support from the U.S. military. So I do think that's an interesting perspective. And maybe the last thing I'll say here is just that I think it's really important that we are thinking about the life cycle impact of these of nuclear technologies, just like all technologies. And Alaska was also home to uranium mining in Bocan Mountain down in southeastern Alaska that has left enduring social and environmental impacts. And we saw the reaction of folks in Western Alaska to proposals for uranium mining in the past couple years. So typically there's a lot of discussion about what happens to the nuclear material at end of life. But I also have to think about, going back to Greg's point with Saskatchewan, where is the nuclear material coming from, and what are the impacts on those communities?
Greg, do you want to go ahead and give us a little bit of background on Saskatchewan and the history with uranium mining there?
Yeah, you betcha. It's so we've had I guess it's coming close to half a century here of or more in terms of development of our uranium resources. So we're always in the top three of uranium producers in the world. We have the highest in terms of ore quality. Nobody competes with Saskatchewan. We have the highest high grade uranium mined anywhere in the world. It's not nobody even comes close. But it's in an area in the Northern Administrative District that was it's about it's a technically a municipality, but it's a region of northern Saskatchewan that's about two-thirds the size of Sweden. Just to put it in perspective of geographic area, it's huge, and 39,000 people live there. So it's not high density, obviously. And the percentage of Indigenous peoples that live in the Northern Administrative District is about close to 87%. So it's the highest percentage of Indigenous people of any jurisdiction. It's actually higher than Nunavut in terms of percentage of Indigenous peoples. But one of the things that the Saskatchewan government did back in the late 1970s, early 80s, is with the surface lease of agreements in northern Saskatchewan, had provisions around community engagement, workforce development, employment targets, etc. And over the decades, you've seen a very strong relationship build up with the companies now, Cameco and Orano, the two largest. Orano's French owned and Cameco's Canadian owned uranium mining companies. And so if you look at the legacy now, looking backwards, in an area with 39,000 people, over the last 2 decades, there's been over $3 billion worth of procurement with Indigenous communities. 50% of the workforce in the uranium mining sector are Northern and Indigenous, which is the highest, I think, anywhere in Canada in terms of Indigenous workforce in the uranium mining sector. And this goes multi-generational now. But other things, and this is a point that Philip and Diane made, was around this issue of trust. And so things like water, and water is always a concern. It is for all communities, but especially Indigenous communities where there's still subsistence economies and fisheries, etc., which are really important. What Cameco does as a company, the water testing is actually done by the Indigenous communities themselves. So they're trained in water testing, but they do the testing. So it's the communities doing the testing and reporting back to their communities, which is really important in terms of the trust factor. And you've had multiple spin-offs from that. What they've done, and it comes up time after time after time in northern Saskatchewan when they do polling around support for the uranium mining industry and nuclear in general, it's always over 70%. I don't think you'll find a jurisdiction as high as that, arguably in North America, and certainly not globally in terms of support for the uranium mining sector. So when we're looking at Saskatchewan to move forward to things like the facility that we will be building in northern Saskatchewan to as we retire our coal-fired plants in southern Saskatchewan and bring on nuclear, is a very high acceptance. And this goes across the political spectrum, left to right. So even our Social Democratic Party in Saskatchewan, which used to be the Natural Governing Party, it's called the New Democratic Party. So NDP is the acronym. But some environmentalists in Canada call the NDP the Nuclear Development Party, just to put it in context in terms of the broad social and political consensus within the province. And so this is a high interest in smaller, the micromodular as well. But that all started because of very wise decisions with the surface lease agreements back in the end of the 1970s that created this foundation of trust and tangible benefits that communities are participating in. It made an enormous difference.
Thanks, Greg. I appreciate it. Travis, going on to you. So I'm very appreciative of somebody from the utility industry here on this panel. You know, I'm curious about your interest in nuclear, in looking at all the different options and choices that we have available to us here in Alaska, how do you think about nuclear from the perspective of a utility manager, within the context of all the different options that we might have moving forward?
Yeah, I think really from my perspective is, especially with the advances in nuclear, both on the MMR and the SMR front, in the recent history in the last 10 years or so, I think it's going to play a major role at some point in time in Alaska. I think Alaska is a perfect place to test this out, especially when you've got various microgrids that potentially could be tested out on the smaller scale, or even potentially on the Railbelt with like an SMR type scale. But I think really from my perspective is looking at nuclear, the fixed cost, or the cost of energy that comes out of it, and being fixed over a long period of time, takes away a lot of that fluctuation and vulnerability that a lot of Alaska communities are seeing right now with oil prices, even natural gas prices. Continuous fluctuation makes it difficult. It makes it difficult for others to want to come into the state and develop industry of some sort when there's no predictability of what those rates are going to be. So for me, that long-term cost of energy is huge. Obviously, the emissions reduction compared to other generation sources we would have for optionality is big for the environment. I also believe that the fact of having some sort of a cleaner base load or available 24/7 type of generation is definitely needed, which was touched about by a couple of the panelists already today. But I think the reservation I have as the utility manager is, at this point in time, it's not quite there yet. Like it's right on the cusp of being out there. We've heard a lot about the Eielson reactor and that going forward. We're keenly watching the process and the progress of that reactor. And is there opportunities for that reactor at some point to be expanded to a larger scale so that it could be utilized on the rail belt? Those are conversations that we're having and looking into to see what that would look like. But also taking a look at it is, a lot of people don't think about the capital cost for a reactor is astronomical, and it's a high upfront capital cost, but your long-term cost of power is quite a bit lower, much like hydro. It's similar that way, to where very capital intensive on the front end, but those costs come down, especially after you pay off your debt service going forward. But it's that, how do you get that financial funding to pay for that? And so I know a lot of conversations I've had with a lot of different folks is, it seems like the developers going from just, I'm selling you a product, to actually running the plant and going into some sort of a power purchase agreement. For me as a utility, that seems a lot more promising to look at that function than to have to look at trying to come up with the capital investment for, it could be $1 billion plus, depending on the size of the plant.
Yeah, I don't know if you had a chance to listen in on Oklo's presentation or not, but that's kind of, what they're really looking at is that kind of providing energy as a service, right? Like, so that they're really the ones that are operating under some kind of a long-term contract with the utility or some other, organization that they're providing power or energy for. And I'm kind of curious, has there been any talk about the potential of actually scaling up the Eielson reactor, since they're looking at the 75 megawatt design now?
There's
I don't want to
been
put you
some
on the spot there.
very preliminary discussions on even if it's even feasible or not.
Yeah.
Because I know, going back to my time at HARP, as when we were a government ran, facility, we couldn't put power back onto the grid unless it was a declaration of emergency. But if it's not necessarily owned by the federal government and it's owned by another entity under a power purchase agreement, there might be some opportunity that could be scaled up and sold back. But it's still very early in the process, and it's unknown at this point if that could happen or not.
Okay. Yeah, I think that would be interesting to look into a little bit more. You do have a couple, I'll stick with you for a second, Travis. You've got a couple of really large mines that are part of your grid that are major baseload customers for your utility. And I'm kind of curious, like, are you getting pressure from them to like decarbonize your energy supply at all? Is that a conversation?
It definitely is, especially mines that may be corporate, their corporate headquarters in a different country. There's a lot of push for the decarbonization for their entire portfolio. So not just Alaska, but everywhere else. So we have seen a lot of questions and a lot of, I wouldn't say pressure, but a lot of encouragement to try to decarbonize because that's their corporate goals and they're trying to find ways to do so. So we've been working very closely with both of our large mines in order to figure out paths in order to do just that.
Greg?
Yeah, I wanted to just jump in on this latter point because Saskatchewan is a mining province. So we're one of the largest producers of potash, but also copper in abundant of rare earth minerals. But this issue about decarbonization, Travis is dead right. Capital moves. Capital moves anywhere it wants to go. And shareholders want decarbonized power. And we're seeing this come in Saskatchewan. We know in the back, and this is why options, whether geothermal, nuclear in particular, is seen quite favorably because shareholders want it. So it doesn't, you might want to look at different portfolio, but it's the old adage, money talks and bullshit walks. And if you don't have capital investment in mining, so when we're looking at energy, we got to be thinking of the whole economy of a state or a province in our case, and not just thinking about what is the cost per kilowatt hour, but what kind of choices we're making that enhances large capital investment in projects like mining we need for the future. So these things, I think Travis is bang on that point.
Go ahead, Phil.
Yeah, absolutely. If I can jump onto this. So I think in Alaska's context, it's really fascinating too, because what Travis said about these high upfront capital costs, this has been the challenge on the Railbelt for 75 years, right? This is why Chugach pivoted to gas rather than big hydro, because they had trouble securing the financing for the high upfront capital of those hydro facilities. And, we can even see this in GVA's history, right? The Healy 1 plant was, originally the GVA board wanted that to be a nuclear facility. And one of the reasons that didn't move forward is because even though the Atomic Energy Commission was promoting the technology, the Rural Utility Service refused to provide financing. So it's really fascinating. There is a tension within the federal government, even on some of these projects. But, back to some of what Greg was saying in this point about social license and the buy-in of the community. I think this is one of the big things that Alaska has been struggling with, not only because of the history of the federal government's involvement with nuclear, but I would also say because of the history of the coal industry in Alaska. And we even saw this when the Eielson reactor was announced. The Air Force took pains to say, look, this is going to be a small reactor. It's not going to displace the existing coal cogen unit here. Coal has played an extraordinarily important role in interior Alaska. It saved our forests because we basically cut down most of our trees, and then coal came in and provided that lifeline. And I think that we really need to take seriously the political economy of coal in Alaska. And, if we're going to see nuclear as baseload units, I see those as displacing coal. And that's a really tricky and difficult conversation. But I also think it's one worth having.
I also be looking at natural gas and being the person sitting in Anchorage where we're getting a fairly dramatic set of, cautions about the gas supply running out, arguments over how many ports to build to bring in liquid natural gas, and the cold snap, which was even more severe, obviously, in Fairbanks, but for us was a pretty, it was the longest cold snap we'd had of that sort, really, since I've lived here. people here are very nervous. Coal right now is, I don't think, on the minds of South Central residents for energy sustainability. And I've heard a lot of people say, why are we talking about nuclear for rural communities? Why aren't we talking about it for the Railbelt? So I think, Travis is probably deep in those conversations about the different views of the different energy providers. We've also got Bradley Lake. We've got a lot of other neither coal nor nuclear options being discussed, but I do think this highlights also some of those regional challenges in the state as we have those conversations.
Yeah, Travis, I don't know
Yeah.
if you could jump in. Oh, sorry. Greg, did you want to say something?
No, I'll wait. I won't forget what I'm going to say.
All right, all right. Travis, I don't want to really put you on the spot, but we are really kind of struggling a little bit with some energy supply issues related especially to natural gas. And it's pretty easy, I think, to always be kind of thinking of replacing you know, a fuel supply with what we already know, what we're familiar with, so replacing natural gas, maybe imported natural gas, maybe we can build a pipeline. But how do you really think about those kinds of like known technologies that have big price tags with sort of like an emerging technology like nuclear? It's really difficult to make any decisions around it right now. You sort of alluded to that, but how can you kind of like think about sort of keeping as much optionality as possible and making sure that you're not locking yourself into a path that may not ultimately, be the best or lowest cost or most sustainable long term when we're looking at, trying to build our economy, when we're looking at kind of our long-term future for the state. It's hard to know what all the answers are, what the future is going to bring. How do you handle that?
That is one of the biggest challenges, honestly, Gwen, that we're dealing with. And to add, I guess, insult to injury on that in a good way is we're also seeing for the first time in decades potential large load increases within the interior Alaska. So one of the things we're really struggling with is we've got aging infrastructure, like you said, some of these legacy type generation, units that are out there, whether it's coal or fossil fuels or otherwise. And how do we plan for the short term, the midterm, and then the long term, looking out the next 10 to 20 years? Because honestly, the nuclear front, if we were to go down that path, you're not going to be online for 10 years. If we pulled the trigger tomorrow, it would be 10 years before it's ready to come online. So what we're trying to do is strategically figure out, okay, what can we do in the short term that's going to meet the needs for now, but is not going to handcuff us to stick with this technology in the future? Same thing with looking out the next 5 to 10 years. Can we do something to where, prime example, if we're going to go buy a new gas turbine right now that we don't have natural gas for an option, but we have a plant right next to our refinery, we're going to probably buy something that's a dual fuel that can be converted to natural gas if the pipeline were to come through. And there's some decisions we're going to have to make possibly before final decisions are made on a gas pipeline. But building the technology to where it can handle multiple fuel sources, also, financing things to where they're paid off before maybe the next technology is here and ready to go. And I think really the big thing we're looking at too is taking a different mindset from the typical utility mindset has always traditionally been, we want to own it, we want to operate it, it's ours, to maybe somebody else could own and operate it and we just pay for that offtake. And so we're, I think, really looking at changing our mindset as well as, do we necessarily need to be the owners of these facilities going forward? So I think that gives us a little bit more optionality going forward as these emerging technologies are coming forward.
Well, that's kind of a general evolution in the utility industry, wouldn't you say, right now? Is like, what is that role of the utility and energy production versus like the distribution of that to customers?
Absolutely.
Yeah. So, well, Greg, you wanted to make a comment, so let me pass it to you.
Yeah, I did. I was just looking in the chat thing. I see Bob had a comment in there about greenhouses and energy security, and this would be with more the micromodular reactor side of things. So I'm assuming that's Bob from Alaska, not Bob from Canada. But so but I'll say we've actually done that modeling, and there's two things about the modeling. One, when you compete, we did this for using the community of Inuvik as a model and just doing the numbers on that, and using the parameters that we had, an MMR can outperform fossil fuel in those conditions because we got to truck in LNG and other resources because it dried up the field in terms of its ability to continuously produce fuel for the natural gas plant in Inuvik. So we're looking at that option. But the beautiful thing about nukes, we talk about it in terms of electricity, but the heat can sometimes be more valuable than the electricity and the usage of heat. And so that's got to be brought into the conversation. And then I was thinking about Travis's. I know he's $1 million man, but these are $1 billion decisions, and and how do you overcome that? And part of our modeling we did was looking at what are the benefits. So of course you're going to be looking a small part of it around your cost per kilowatt hour. You know what's your ROI and what's the length of it, and it does scale very similarly as Travis said to hydro. But but when we start doing input-output analysis and looking at these economic linkages, not just regionally, but when you think, some of the production could be in Pittsburgh, think Westinghouse and others. It's one that we're working, folks in Saskatchewan, we've worked with. Then you model out what are those at the regional, say a local, state level, and national, and then you factor in the benefits in the economy of that. It pencils out differently in terms of who those investors might be, including federal government sources, and it might be consumers of heat that might require, and so on, to package that together. So I just raised that, but it was actually Bob's point about greenhouses. And here's the interesting thing around MMRs, they actually are not very good in terms of generating direct employment. So we got to be realistic here, especially locally, especially in more remote. But what they do, and this comes to the greenhouse, you can create a lot of good jobs that have that are labor in terms of the threshold for entry into the workforce, in a labor force readiness, in terms of running a greenhouse and having more people working, creating that food security, creating better health outcomes, creating people that have got to truck it, say, or barge it or whatever, fly it. I guess you aren't going to be barging tomatoes; they'll be froze to nothing by the time you get them there. But you know what I mean. But that whole supply chain creates a lot of employment that's not directly to the generation of the power itself, but the economies that you can create because you have, as Travis identified, that stability and predictability. And that's massive for investment. Even if there's a slight premium, but you have predictability of pricing, that's a game changer for capital investment in other parts of the economy. And one last point, I see Nicole Jacobs is on here. All of us well, Philip's a little bit younger, but the rest of us, I can see Gray and Travis is here. But but the rest of them are a bit older. But I'll tell you, an up-and-comer, which I think is a bright star you guys have at University of Alaska Fairbanks, is Nicole Jacobs. So pay attention to her work as it's coming out.
Yeah, Nicole, it's been really fantastic to work with. So Diane?
Yeah, so I wanted to circle back actually to Gwen, where you started the part of your question to me that I didn't answer, and bouncing off something Travis had said. I think one of the questions I have, and I know others have, is are we looking at nuclear as the long run answer? Or is nuclear actually going to end up being a transitional stepping stone? Because there's other technologies, right? I know very little other than from what I've listened to my colleagues talk about with hydrogen, but I know there's a lot of development happening, a lot of interest in hydrogen. There's also, of course, better batteries. So that question about what's the role of renewable energy? Well, a lot of what's holding back renewable energy is what we do with the excess energy that's being created when it's sunny or the wind is blowing, to have that available to us when it's dark and calm. So so I also, I have no answer to this at all, but I do think there's this question about if these reactors have a lifespan of somewhere between 10 and 30 years, and they're going to come online 10 years from now, what are we looking at 40 or 50 years from now? Will we have something else that makes this current swath of nuclear development, I don't know if I'd say irrelevant, but certainly
we'll have nuclear fusion by then.
we'll have fusion, or maybe we will really have moved to something. I mean, and to Greg's point, batteries require mining as much as nuclear does, but so making sure we can have mines that have power in order to have the materials to develop the next generation is also important. But I try to keep that in mind, because when a lot of people look at that huge investment up front with nuclear, is that something we're going to have to do repeatedly, or is this really, we have to decarbonize, and that is critical, urgent. We are way behind the curve. So can we do this now while we figure out what's next?
Does anyone want to make any last comments here? We've just got a few minutes left in the whole webinar. That time went really fast. Phil, go ahead.
Yeah, just thinking about the history of this and thinking about other competing fuels. One of the things that one of the arguments that I make in my paper on the history of nuclear power in Alaska is that coal has without a doubt created more human and environmental harm for Alaskans. Yet historically, nuclear power has been perceived as far more dangerous. So I have to think, we really need to look at it's not just the social license, it's the social perception of risk versus how safe are these technologies based on the evidence, right? And really weighing those two things, because those are two very different factors that we need to think about. And then finally, I would just offer a prediction, which I don't usually do as a historian. We prefer to be safe and comfortable in the past, but I think to the extent that we are going to see nuclear in Alaska over the short and medium term, we're going to see it on we're going to see it on military facilities, right? It is going to be an extension of that history, and it is going to be a much harder bridge to make this a civilian technology. And I think that comes with a tricky trade-off that the federal government is assuming more of those upfront risks. But what does that mean about social license and the ability of the public to weigh in on that? That's a big question.
Anyone else? Travis, do you have any last words? Any thoughts?
No, I would piggyback with what Phil said there. I think really one of the challenges that we will have to integrate nuclear anywhere in Alaska is really the education of our communities. And that was the one thing that I think was always the hurdle, even when I was going through this process and having dozens of public meetings down at Copper Valley, was there was always three things that came up, or three buckets. It was safety, security, it was environmental impact, and then it was waste disposal. And with a lot of the modifications and changes in technology for the SMRs and MMRs, the first two buckets were more or less addressed, but it always was the waste disposal. So I think that's always going to be a challenge until that is figured out. So it's going to be a challenge. I think it really comes down to we need to really work on educating our fellow Alaskans and others to really understand where it's at and where it needs to go before you get that buy-in.
Yep, agreed. All right. Well, I really appreciate all of you joining me. That panel went by incredibly fast, so thank you. And thank you really to all of our presenters and attendees who kind of stuck with us and joined us for at least today for the Beyond the Basics, the potential role of advanced nuclear in Alaska. I'm hoping everybody learned something that they didn't know before they came here. I definitely did, and certainly a lot of food for thought. I'm hoping that we can kind of continue these conversations with the Alaska Nuclear Working Group for those of you that are interested. And I really hope that that's a forum for really diverse perspectives. We really want to bring people that have really, have questions. So we want to get those questions answered, because we couldn't get all of them that have been dropped in the chat answered through the course of the last 2 days. And I want to especially thank our national lab partners. I think some of them are still online. I know a lot of them that didn't speak also joined us, and I really appreciate their the attention that they've paid to Alaska and what great partners they've been in terms of just answering questions and being available. So thank you to all of them. The recordings for all our previous workshops and for this one are available on the alaskasustainableenergy.com under virtual workshops. And this one should be up within a couple of weeks. 30 days is the most. And we'll try to get as many of the presentations posted there as possible. I know I was pretty interested in looking at Botros's today too, and wanted to spend a little more time with some of those numbers as well. I think they're dropping the link to the workshops in the chat right now. We are going to send out a short survey following the workshop. We would really like your feedback on that. It's important for us to help us improve the future workshops. And so you can access the survey by scanning the QR code on the screen right now, clicking the link in the chat if you want to do that. But that's very helpful to us. And our fourth and final workshop of this series, Alternative and Synthetic Fuels for Energy and Transportation Systems, is going to be April 1st and 2nd. Another topic that was a little bit by request from previous audience participation. And so that one's going to explore the potential role of alternative and synthetic fuels across energy and transportation systems, with particular relevance for Alaska's geography, climate, and reliance on fuel-intensive infrastructure. The session is going to take a pretty broad view of emerging fuel pathways, recognizing that solutions may span aviation, marine and ground transportation, and stationary energy as well. All right. I'm not going to read everything about that, but you can go ahead and register. All these workshops are free, so you can register now on the Alaska Sustainable Energy Conference website. And of course, we hope to see all of you at the main conference in person at the Denina Center in Anchorage, May 19th through the 21st, 2026. That is not free, but tickets will be available soon on the website. So thank you for joining us for Beyond the Basics, the Potential Role of Advanced Nuclear in Alaska virtual workshop. And one final reminder before you go, please join the Alaska Nuclear Energy Working Group. It's going to be a really good forum for getting more of those questions answered. Fill out the survey so we know what you're interested in. The first meeting is going to be on February 24th, and it's going to be on waste disposal, because that is a topic, as Travis just alluded to, that there's always been a lot of interest in. So you can sign up and let us know what you're interested in hearing there by scanning the QR code. And thank you. That's all we have. Have a great afternoon, evening, whatever time zone you're in. And thank you very much for joining us.